Hey everyone! Welcome to the course on C++ memory management. Get ready to level up your coding skills as we dive into essential topics like memory allocation, smart pointers, and resource management techniques. Throughout this journey, you'll get your hands dirty with some engaging coding exercises, and don't forget to check the description for a link to our GitHub repository where you can access all the code we'll be working with. So make sure to stick around until the end where you'll tackle a final project that puts everything you've learned to the test. Let's jump right in and get started. Memory in C++ is fundamentally about managing sequences of contiguous bytes that your program can utilize. Now, this might sound a bit dry, but understanding how memory works is absolutely crucial for writing efficient and effective C++ code. In this tutorial, we're diving into how memory representation in C++ functions, exploring the various types of memory you'll encounter, and discussing how to manage this memory effectively. So, grab a snack, settle in, and let's get started. Now, let's take a look at a basic example of variable declaration and memory allocation in C++. In this snippet, we declare an integer variable named x and initialize it with the value of 10. This allocation reserves a specific amount of memory for x on the stack, allowing the program to store and manipulate this value easily. To illustrate how we can monitor memory allocation, the code utilizes the address of operator AND, which retrieves the memory address of variable x. When you execute this line, it will print out the actual address in memory where x is stored. Understanding how to access this address is vital as it lays the groundwork for more complex memory management concepts. Alongside this, the code also outputs the value of x, showing that yes, we can easily work with the data stored in that memory location. This simple example not only teaches the fundamental concept of memory representation in C++, but it also sets the stage for deeper exploration into how variables are managed within different memory regions. Now, let's dive into implementing dynamic memory allocation in C++ using the heap. To start, we'll include the necessary headers and set up our main function. Inside this function, we'll first allocate an array of 5 integers on the heap with the new operator. This is fantastic because it allows us to define an array size that can be determined at runtime, especially handy when we aren't sure how big the array needs to be until our program is running. Next, we'll initialize this array by doubling the index values, which demonstrates just how easily we can manipulate elements stored in dynamically allocated memory. After that, we'll loop through and display each element of the array, showcasing the simplicity of accessing and using these elements through their indices. Finally, it's super important to free the memory we allocated once we're done using it. This is where the delete square operator comes into play. This cleanup step is essential to prevent memory leaks, which are a common pitfall when working with dynamic memory. By managing our memory properly, we'll ensure our program remains efficient and stable, balancing flexibility with responsibility in C++ memory management. From these values, the pie chart titled Memory Representation in C++ divides the subject into 6 labeled slices with the following proportions: stack memory 30%, heap memory 25%, pointers 20%, dynamic allocation 15%, memory leaks 5%, and smart pointers 5%. From these values, we can draw several conclusions. Now, stack memory is the single largest slice at 30%, and when we combine that with heap memory at 25%, we get a total of 55%. This indicates that raw storage regions form the majority of the representation on this chart. Next, we have pointers at 20% and dynamic allocation at 15%, which together make up 35%. This highlights that addressing and allocation mechanisms are the next most significant concerns in memory management. Memory leaks and smart pointers each occupy 5%. Now, you might think, oh, that's small, but they represent distinct topics. Memory leaks focus on a common failure mode, while smart pointers offer a mitigation and ownership strategy. Overall, this chart suggests a natural learning progression. First, prioritize understanding the stack and heap layout, then delve into pointers and allocation semantics, and finally, address leak prevention and smart pointer usage to manage ownership and lifetime effectively. This roadmap will definitely guide you as you navigate the complexities of memory representation in C++. Now, let's take a closer look at how pointers work in C++. In this example, we're going to start by declaring an integer variable, which we'll call value, and we'll set it to 30. Next, we introduce a pointer, ptr, which is initialized to point directly to the address of value using the address of operator. That's the ampersand. This example makes it clear how pointers give us a way to reference the exact location of a variable in memory. Now, here's where things get interesting. By dereferencing the pointer with the asterisk operator, that's the asterisk ptr, we can access the value stored in value. This concept is crucial, as it shows us that pointers allow for indirect manipulation of data, which can lead to more flexible and powerful programs. Also, if we print the pointer ptr, we'll see the address of value, showcasing how pointers serve as essential tools for memory management. So, this example not only illustrates the basics of using pointers in C++, but it also dives into the core principles of memory manipulation, a vital skill for any C++ programmer. Understanding pointers means you can handle and manipulate data efficiently, but a word of caution, mishandling pointers can lead to some serious errors and crashes. Always be careful with pointers as you dive deeper into your programming journey. Next, we will write the following code to illustrate a common problem in C++, and that problem is memory leaks. In this example, we have a function called createMemoryLeak. Now, what this does is it allocates memory on the heap using the new keyword for an integer pointer named leak. But here's the kicker. It doesn't free this memory using delete. Each time createMemoryLeak is called, it creates a new integer without any corresponding deallocation. This leads to increasing memory usage over time. Moving on to the main function, we've got a loop that iterates 1,000 times, repeatedly calling createMemoryLeak. This really exemplifies a scenario that could happen in a larger application if memory isn't managed properly. As a result, the program ends up with a whole bunch of allocated but unfreed memory blocks, which means we've created memory leaks. Now, the output, memory leak created, serves as a reminder of this issue, highlighting just how crucial it is to manage memory carefully. To prevent such leaks, developers should always ensure that any memory allocated with new is matched with a delete, or, preferably, use smart pointers that automatically handle memory deallocation when they go out of scope. This code effectively highlights the potential pitfalls of C++ memory management and reinforces those best practices we should all be following in programming. Now, let's take a closer look at how std_unique pointer works in real-life applications, which is really a key player in modern C++ memory management. First things first, let's include the necessary headers. We need std_memory for smart pointers, and don't forget std_iostream for our output. Now, we'll declare a unique pointer called p1, and it points to an integer set to 10. This is a great way to show how unique pointer takes care of dynamic memory all on its own, allocating memory right there on the heap. Next up, let's use count to display the value that p1 is pointing to. You'll see that dereferencing it gives us the value, and we don't even have to worry about manual memory management. Now, here's where it gets interesting. The unique attributes of unique pointer really shine when we want to transfer ownership. To do this, we use the move function. By assigning P1 to another unique pointer named P2, we've effectively transferred ownership, which means P1 is now empty. This feature prevents multiple pointers from referencing the same resource, which is a huge bonus for reducing the risk of memory leaks and dangling pointers. So, in a nutshell, std_unique pointer not only simplifies memory management, but it also upholds the principles of object ownership, making it an incredibly powerful tool for C++ developers. Next, we will write some code to dynamically allocate an array of integers on the heap. This helps us store multiple values efficiently. First, let's declare a constant integer, size, which will define how many elements our array will hold. So, using the new keyword, we can allocate memory for this array. And we'll call our pointer myArray, which points to that newly allocated memory block. After we've set up our array, we'll initialize its elements in a loop, assigning each index a value that's a multiple of 10. This not only populates our array, but also lets us access each element using pointer arithmetic. Pretty handy, right? Since the memory layout is contiguous, it makes our job easier. Following that, we'll use another loop to output each value to the console, showing just how straightforward it is to iterate through and access those array elements. And here's a crucial tip. Once we're done, we must remember to free the allocated memory using delete dash. This step is vital to prevent memory leaks, an essential part of manual memory management in C++. So, by efficiently allocating and deallocating memory, we ensure that our applications run smoothly and responsibly. Now, let's dive into a class that shows us how to manage memory effectively using constructors and destructors in C++. Here, we're defining a class called myClass, which comes with a dynamically allocated array of integers. The constructor of myClass takes one integer parameter that tells us the array size, using the new operator to allocate memory for this array. This means we can store a list of integers whose size we decide at runtime, not during the compile time. Pretty neat, right? So, when we create an instance of myClass, the constructor kicks in to initialize the array, filling it with values based on their indices. This dynamic allocation, it's a powerful feature. Now, what about cleaning up after ourselves? That's where the destructor comes into play. It's called automatically when our object of myClass goes out of scope, freeing up the memory we previously allocated. This is super important to prevent memory leaks, which can really bog down your program. Finally, to see what's inside our array, we've got a method called display. This method outputs the contents of the array easily. By putting memory management directly into the class, we're making sure resources are handled properly throughout the object's lifecycle, which is a key element of programming in C++. Not only does this keep our code clean and manageable, but it also highlights the crucial role of resource management in C++. As we've explored how memory representation works in C++, it's become clear, thoughtful, that having a solid grasp on memory management is key to crafting efficient and robust applications. From understanding stack and heap memory to the careful use of pointers and ultimately leveraging smart pointers, each area lays the groundwork for mastering how to use C++ memory effectively. So, embrace this knowledge and practice with examples related to memory management. You'll find yourself becoming quite adept at it in no time. Just a friendly reminder, with great power comes great responsibility. And when it comes to C++, that responsibility really means keeping your memory in check. So, happy coding! Now, let's take a look at how we can implement a circle class in C++. This class will feature a public member called radius, and it comes with a constructor that initializes this radius when an object of the class is created. This constructor takes a double as its argument, and using an initializer list sets the radius accordingly. Furthermore, we define a method named getArea, which calculates and returns the area of the circle using the formula pi r squared, where r is the radius. In the main function, we create an object of the circle class named myCircle, passing the value 5.0 as the radius. Now, keep in mind that memory for myCircle is allocated on the stack. After that, we use code to display the area of the circle by calling getArea on myCircle. By running this code, students can see how encapsulation works, attributes and methods are bundled together, and they learn about object instantiation and memory allocation in C++. This example really emphasizes the relationship between an object's attributes and behaviors, showcasing a fundamental aspect of object-oriented programming in C++. Now, let's explore how to retrieve an object's address in memory. In this example, we create an instance of the circle class, which we'll call myCircle, and we initialize it with a radius of 5.0. This instance lives at a specific location in memory, and we can access that location using the address of operator, AND. So let's add a line to our code that prints out the address of myCircle. This little tweak allows us to visually explore how objects are stored in memory, which is super important as we become more familiar with memory management and pointers in C++. Now, when we run this program, it first calculates and shows the area of the circle, and then it reveals the address where myCircle is stored in memory. This dual output really highlights the relationship between an object's data and its memory address, illuminating essential concepts about objects in C++. Understanding object addresses not only helps us grasp object lifecycles, but it also sets us up for tackling more advanced memory manipulation and coding efficiently in C++. The accompanying bar chart titled Understanding the Fundamental Properties of Objects in C++ reveals the relative importance assigned to 6 core concepts related to objects, and let me tell you, it's pretty telling. So take a look at this. We have object lifetime coming in at 25%, memory management at 20%, and then we've got pointers, encapsulation, and inheritance all tied at 15%. And finally, polymorphism rounds it out at 10%. The y-axis stretches from 0 to 30%, and each bar is clearly labeled with its percentage, making understanding the ranking pretty straightforward. From what these numbers show, object lifetime is clearly the star of the show here, right? Followed closely by memory management, which, let's be honest, is crucial since both the duration of an object's existence and how its resources are managed are fundamental concerns when programming. Now, pointers, encapsulation, and inheritance, they're all sitting comfortably at that intermediate level, each representing the same 15% of importance, indicating they're equally vital in practice. Now, polymorphism, while still significant, is emphasized the least at 10%. So this clear order, backed up by exact labels, really illustrates something important. We should prioritize managing object lifetime and memory in C++ design and implementation first. Then we can focus on pointers and class design, which includes encapsulation and inheritance. And finally, we can give some thought to that polymorphic behavior, though it's comparatively smaller in this context. Now, let's implement the following code that builds upon our circle class by adding the ability to modify the radius of the circle after it has been instantiated. We're introducing the setRadius method, which allows us to change the value of the radius attribute directly. In the circle class, we define a public method called setRadius, which takes a double parameter. This method assigns the new radius value to the existing radius attribute of the circle object. By encapsulating both data and behavior in our class, we ensure that any modifications to the circle's radius can be done safely through this method, reinforcing the principles of object-oriented programming. Now, within the main function, we create an instance of the circle class called myCircle, initializing it with a radius of 5.0. Let's display the initial area of the circle using the getArea method. Following this, we modify the radius by calling myCircle.setRadius with a new value of 10.0. And finally, we'll print the area again. This demonstrates how we can change an object's state while retaining its identity, similar to how we might change a pet's name without relocating it. Now, let's explore memory allocation further with an example of both stack and heap allocation using a circle class. In this code, we defined a circle class that has this single-member variable, radius, and it includes a constructor to initialize this radius along with a destructor to display a message when the object is destroyed. Next, we create an instance of circle, let's call it stack circle, and this one is allocated on the stack. This means it will be automatically destroyed and its destructor will be called as soon as it goes out of scope at the end of the main function. And you see, this demonstrates the stack's automatic memory management, which is kind of nice. In contrast, we have another instance of circle, let's refer to it as heap circle. This one is dynamically allocated using the new keyword, which places it on the heap. Now, here it's essential to manage memory manually, so we need to explicitly call delete to free the allocated memory for heap circle. You know, this example really illustrates the importance of understanding object lifetime. Where the stack offers automatic cleanup, the heap requires diligent memory management to avoid leaks. So, through this, you'll really appreciate the responsibilities that come with dynamic memory allocation in C++. Now, let's implement some enhancements to our circle class. We're going to add a copy constructor and an assignment operator, which are really crucial for managing memory efficiently. So, the copy constructor is invoked whenever we create a new instance of circle from an existing one. This allows us to create a fresh copy with the same radius, ensuring that each circle has its own copy of the radius attribute. This is super important because it helps us avoid issues like sharing the same memory address. It can lead to problems such as double deletion later on. Next up, we need to define an assignment operator. This comes into play when we assign one circle object to another after they've already been created. The operator starts by checking if both objects are different. This way, we steer clear of unnecessary operations and any potential memory conflicts. By only copying the radius when it's absolutely needed, we prevent memory leaks and ensure resource integrity. Now, if we take a look at the main function, creating circle B using circle A actually invokes that copy constructor, while assigning circle C to circle A triggers our assignment operator. This illustrates just how these methods work to manage resources for dynamic object manipulation. Trust me, this setup is absolutely vital for working with more complex classes in C++. Now let's implement polymorphism, a vital concept in object-oriented programming that enables the same interface to be used for different underlying forms or data types. We're going to create a base class called shape, where we'll declare a pure virtual function called getArea. This makes shape an abstract class, which means you can't actually create an instance of shape directly. It's designed to serve as a blueprint for other classes that derive from it. Next, we'll derive two classes from shape, circle and square. Each of these classes will implement the getArea method, providing their specific formulas for calculating area. For instance, in the circle class, you'll define it to take a radius and use pi r squared to calculate the area. Meanwhile, the square class will calculate the area based on the length of a side using s squared. Now, in the main function, we will create pointers of type shape that point to instances of circle and square. This allows us to call the getArea function on each shape without needing to know their specific types at compile time, thanks to polymorphism. And finally, we'll make sure to clean up our dynamic allocations with delete to avoid any memory leaks, which is super important for memory management in C++. Wrapping up our exploration of the fundamental properties of objects in C++, it's essential to realize the balance between efficiency and safety. Understanding how objects interact with memory, their life cycle, and behaviors can significantly help you make better design choices. You've now built a solid foundational knowledge, empowering you to confidently create and manipulate objects, manage their memory responsibly, and effectively utilize key object-oriented principles like encapsulation, inheritance, and polymorphism. As you continue your journey with C++, remember to keep practicing and experimenting with object-oriented design patterns. The more you apply these concepts, the more intuitive they'll become. So, happy coding! Now, let's take a look at how we can implement our naive string class, which really highlights the core concepts of dynamic memory management in C++. This class starts off with a private member, p, defined as a pointer to char, which will hold our dynamically allocated string. So, in the constructor, we take a C-style string as input and allocate sufficient memory on the heap to store that string. Don't forget, we also add an extra byte for the null terminator. By using new, we ensure that the memory is allocated dynamically, really aligning with our focus on resource management. Next, we copy the input string into that allocated memory using the strcopy function. This is crucial because it ensures that our naive string has its own copy of the string data instead of just referencing the original C-style string. Now, it's important to talk about cleanup as well. We must define a destructor for our class that will handle releasing the allocated memory when the object goes out of scope. So, by invoking delete dash on P, we effectively prevent memory leaks, which is absolutely a critical aspect of memory management in C++. This careful construction demonstrates the real importance of having proper cleanup logic to maintain efficient resource handling within our application. The displayed figure titled Key Concepts in Resource Management presents a bar chart where the x-axis lists 5 distinct concepts: destructor importance, memory leaks, dynamic allocation, object lifetime, and resource management. Meanwhile, the y-axis quantifies each concept's importance level %. Each bar is annotated with its exact numeric value above it. Destructor importance at 80%, memory leaks at 60%, dynamic allocation at 75%, object lifetime at 90%, and resource management at 85%. So, what can we conclude from these values? Well, first and foremost, we see that object lifetime is rated highest at 90%. This indicates that controlling when objects are created and destroyed is viewed as the most critical aspect of resource management. Right behind it, we find resource management at 85%, which emphasizes the broad responsibility of classes to handle resources correctly. Now, destructor importance, sitting at 80%, underscores the need for explicit cleanup logic. This is something we really saw in our naive string destructor example. And then we have dynamic allocation at 75%, highlighting that allocating memory on the heap is a substantial part of the problem space we're dealing with. Even though memory leaks come in at 60%, which is numerically lower than the others, it still represents a significant concern, suggesting that while leaks are indeed something we need to prevent, our chart emphasizes proactive design elements like object lifetime and resource management more strongly than it does the leaks themselves. Taken all together, these plotted values reinforce a very important lesson. We must prioritize clear ownership and lifetime semantics, and ensure that destructors, or even automatic mechanisms, handle cleanup to avoid the practical consequences represented by those memory leaks. Now, let's take a look at how we can implement a simple, naive string class that manages dynamic memory. This class features a private member, p, which is essentially a pointer to a dynamically allocated array that holds our string. So, When we create an instance of naive string, using the constructor that takes a C-style string as input, we allocate memory with the new operator based on the length of the input string. Next, we recognize the significance of proper memory management by incorporating a destructor. Although it might seem like we can skip it, a destructor is crucial for cleaning up the allocated memory when the object is destroyed. This cleanup is done through the delete shell operator, which we must invoke on P to avoid memory leaks when our class instances go out of scope. Through this approach, we're highlighting a fundamental principle in C++ resource management. It's vital to ensure that whenever we allocate resources, we also define a clear strategy for their deallocation. As we proceed, we'll further elaborate on how encapsulating this functionality correctly guards against memory mismanagement, showcasing the essential role destructors play in maintaining system performance and stability. All right, let's dive deeper into this concept as we explore practical examples. Now, let's see how we can expand our naive string class with a copy constructor and an assignment operator to enhance our resource management. In this implementation, the copy constructor ensures that when we create a new instance of naive string from an existing one, it allocates its own separate memory for the string. This is crucial to prevent multiple objects from sharing the same memory address, which could lead to issues if one object deallocates the memory first. Now, moving on to the assignment operator, before we assign a new value to an existing instance, it first checks for self-assignment to avoid unnecessary operations and potential errors. If the object isn't self-assigning, it will delete the existing memory allocation to prevent memory leaks, then allocate new memory for the incoming string from the other instance. This method helps ensure that the class maintains proper memory management throughout its lifecycle. And finally, we include a destructor that deallocates the memory pointed to by P when the object is destroyed. This three-part approach, combining the copy constructor, assignment operator, and destructor, forms the well-known rule of three in C++, which is essential for maintaining resource integrity in any class that manages dynamic memory. Now, let's dive into how we can implement a function to display the contents of our naive string class. The displayString function is carefully designed to take a constant reference to a naive string object as its parameter, which ensures that it doesn't modify the original string while providing efficient access to it. Inside this function, we utilize the get method, the one we assume is defined in our naive string class, to retrieve the character pointer that holds our string data. When we call this function, it outputs the string to the standard output using stdcout, followed by a new line. This approach not only encapsulates the behavior of displaying the string, but also reflects how well our class manages resources, keeping functionality clean and user-friendly. By using a constant reference, we ensure that the contents of the string are displayed without unnecessary copying, which really enhances efficiency. As we continue with our implementations and put the functionality of naive string to the test, this display function will become essential in validating that our resource management strategies are working as intended. It reinforces all those principles we've learned about effective memory handling, and, trust me, it's really key to our progress. Now, let's implement the naive string class using smart pointers to enhance memory management. In this version, we utilize stb unique pointer, which automatically handles memory cleanup when the naive string object goes out of scope. The class features a private member, P, that stores the unique pointer to a dynamically allocated character array. In the constructor, we allocate memory for the string using new char stringlen str plus 1, ensuring that we're copying the content of the provided C-style string into this allocated memory. By using p.get, we retrieve the raw pointer to pass to str copy, which lets us fill the allocated array with the string data. Now, here's the real beauty of this design. It eliminates the need for a manual destructor, since std_unique pointer automatically frees the memory used by p when naive string is destroyed. This significantly reduces the risk of memory leaks. Additionally, we've included a display method that neatly prints the string stored in our unique pointer. By implementing resource management with smart pointers, we simplify our code and ensure a safer memory handling strategy, while allowing us to focus on higher-level functionality. Now, let's take a closer look at a simple implementation of the person class, which really illustrates some key concepts of object lifetime and special member functions. This class has a constructor that initializes the object's name and prints a message when the constructor is called. And this reinforces the idea that constructors are responsible for setting up resources right when the object is created. Next, we define a destructor that performs cleanup when an object goes out of scope, which shows how automatic objects manage their own memory, like they invoke the destructor when needed. This is super important for maintaining resource management in C++. Now, the createPeople function is where we see 3 person objects being created. Let's call them Alice, Bob, and Charlie within its scope. Here, we can observe that the constructors are called in the order they are created, while the destructors, they actually get called in reverse order when the function exits, emphasizing that last in, first out, or LIFO principle. Finally, as the main function invokes createPeople, we get to observe the entire life cycle of these objects in action. And this really emphasizes the importance of understanding how constructors and destructors work together within the scope of automatic objects. This concept is fundamental knowledge for writing safe and efficient C++ code. Now, let's examine the implementation of the copy constructor in the naive string class. This special member function is essential for creating a new object as a duplicate of an existing one, ensuring a deep copy of the string data. So, in the code, we allocate memory specifically for the new object's character array. We're using new char here, which ensures that it has its own separate memory space, preventing any interference with the original object. Now, we copy the string content from the other object to the newly created object using strcopy, which prevents issues such as double deletion when the objects go out of scope. Next, let's write an example function that triggers the copy constructor. In this snippet, we create a naive string object called str1, initialized with hello. When we declare str2 and assign it to str1, the copy constructor is invoked automatically, copying the content of str1 into str2. This highlights how copy constructors effectively manage resource ownership. Essentially, each string now has its own copy of the data, so there's no concern over shared pointers or memory access issues. Now, let's take a look at the implementation of the copy assignment operator. This operator is crucial when assigning one existing object to another. It first checks for self-assignment to avoid unnecessary work, and if they are different objects, it safely deletes the previously allocated memory for the destination object. After that, it allocates new memory and copies the data from the source object. This careful management of resources is what prevents memory leaks during assignment operations. Sigh of satisfaction. Now, let's delve into the implementation of the move constructor. This special member function allows us to transfer the ownership of resources from one object to another, which is a great way to optimize memory management and enhance performance. In our naive string class, we define the move constructor to accept an R-value reference, indicated by the and syntax. The constructor then initializes the new object's pointer to the resource of the other object, effectively handing over ownership. To avoid any dangling pointers, we set the other object's pointer to null pointer. This step ensures that the moved from object remains in a safe state, preventing any accidental misuse. Next, we'll write the logic to demonstrate move semantics in action with the createString function. Here, we create a temporary naive string object named temp with some content, and as we return it, the move constructor is invoked. This shows us how resources are efficiently moved rather than copied, which is particularly beneficial when dealing with large resources. Finally, let's take a look at the move assignment operator, which follows a similar pattern. It ensures that if we're assigning a new resource, we first release any previously held memory before taking ownership of the new resource. This careful code structure prevents memory leaks and contributes to more efficient application performance. So, what does this all mean? Well, memory safety leads the pack. Reminding us that ensuring safety, like avoiding memory leaks, dangling pointers, and undefined behavior, is our top priority. Now, if you look closely, constructors and destructors make up a significant chunk together, around 41.6%, illustrating that correctly handling the creation and cleanup of an object's lifetime is almost as critical as that safety aspect. Next up is the move constructor, which claims about 19.0%, emphasizing the need for efficient resource management through move semantics. And while the copy constructor sits at the smaller slice, 16.7%, it's still important to acknowledge. It indicates that copying isn't irrelevant. It just takes a back seat to those other critical aspects. So, when we look at the chart as a whole, it paints a picture of balanced priorities. First, make sure to guarantee memory safety. Second, implement robust constructors and destructors. Third, prefer using move semantics where you can to dodge those pricey copies. And lastly, handle copying intentionally when it's necessary. Now, let's dive into creating a buffer class that efficiently manages a dynamic array of integers while keeping key resource management principles in mind in C++. This class starts with private members to store the size of the array and a pointer to the dynamically allocated memory. The constructor takes care of initializing these members, allocating memory for the array when a new buffer object is created. Next, we need to ensure we have proper copy behavior, which means we'll implement a copy constructor. This one creates a new instance by doing a deep copy of the data from another buffer object, preventing shared pointers and any potential memory issues. And to complement this, we also need a copy assignment operator. First, we check for self-assignment, then we clean up any existing memory, and finally, we allocate new memory as necessary. Now, to enhance performance and improve resource management, we'll also introduce move semantics with a move constructor and a move assignment operator. The move constructor will transfer ownership of the data pointer from a temporary object to the new instance, which helps to avoid any redundant memory allocations. Similarly, the move assignment operator allows for those efficient resource transfers while ensuring the moved from object is left in a safe state. Finally, don't forget about the destructor. It's crucial for cleaning up that dynamically allocated memory to prevent memory leaks. This wraps everything up nicely within the rule of 3, producing a coherent design that helps foster stable and efficient applications. As we wrap up today's lesson, it's essential to remember that understanding object lifetime and special member functions is not just an academic exercise. These principles have a direct impact on how efficiently and effectively you can manage resources in real-world C++ applications. Proper implementation of these concepts will save you significant debugging time while enhancing the performance and reliability of your applications. Always be mindful of resource ownership and manage it correctly with the right member functions, whether you're constructing, destructing, or transferring resources. Embrace these concepts as you dive deeper into C++, and you'll find yourself writing more efficient and error-resistant code. Keep experimenting with these ideas, practice writing classes inspired by your newfound knowledge, and never hesitate to revisit these principles as they will serve you well throughout your programming journey. Happy coding!
Object lifetime management in C++ is a fundamental concept that every programmer should master. When working with C++, understanding how and when objects are created and destroyed will help you manage resources more effectively and prevent memory leaks. In this segment, we will dive into the details of automatic objects and how they are destructed at the end of their scope, shaping our approach to memory management in C++. Now let's take a look at a simple function demonstrating the concept of automatic objects in C++. In the code, we define a function named createObject, within which we declare an integer variable and assign it a value of 5. This variable is an automatic object, meaning that its lifetime is tied to the scope of the function. As the function executes, we print the value of a to the console, which will display value of a 5. Importantly, once the function completes its execution, it goes out of scope and its destructor is automatically invoked. This automatic destruction releases any resources associated with without requiring explicit cleanup from the programmer. Attempting to access a in the main function results in an error, as it is no longer accessible outside of its original scope. This functionality exemplifies the efficiency of automatic object management in C++, reducing the risk of memory leaks and ensuring resources are freed when they are no longer needed. By utilizing automatic objects wisely, you can write cleaner and safer code while maintaining effective resource management in your applications. Now let's take a look at a practical example of resource management using a class that dynamically allocates memory. In this implementation, we define a class named resource, which has a constructor responsible for allocating an array of integers on the heap. When the resource object is created, the constructor outputs a message to indicate that the resource has been allocated. Next, the class also includes a destructor, which is a special member function that gets called automatically when the object goes out of scope. The destructor's role is crucial. It releases the dynamically allocated memory back to the system using the delete operator to avoid memory leaks. As a result, when we define an automatic object raise of type resource in the createResource function, it gets constructed and assigned the memory. Once the function execution completes, raise is destroyed, triggering the destructor, which deallocates the memory and outputs a message confirming the resource's deallocation. This example illustrates how RAII, resource acquisition, is initialization. Principles ensure proper resource management, making automatic objects convenient and efficient for developers. Now let's take a look at how we can implement heap allocation in C++. In this example, we define a class called resource that allocates an array of integers dynamically in its constructor using the new keyword. This allocation is crucial for managing memory manually, as it allows us to create objects with lifetimes that extend beyond the scope in which they were created. However, because this memory is allocated on the heap, it must be explicitly freed to prevent memory leaks. The class includes a destructor that uses the delete operator to release the allocated memory when the object is destroyed, ensuring that resources are properly managed. In the createResource function, we instantiate resource on the heap by declaring a pointer and assigning it a new resource object. At this point, it's essential to remember that without calling delete on the pointer, the memory will not be freed, leading to leaks. Finally, when the function ends, we call delete on the raise pointer to free the memory, demonstrating manual resource management. This pattern emphasizes the responsibilities of the programmer in handling dynamic memory in C++, contrasting with automatic objects, which clean up resources automatically at the end of their scope. Now let's take a look at how we can manage dynamic memory more safely using smart pointers, specifically STD, unique PTR. In this example, we define a class resource that allocates an array of integers using dynamic memory allocation in its constructor. This allocation is crucial for managing data that requires a lifecycle beyond the scope of a single function. When we create a STD, unique PTR resource, it takes ownership of the dynamically allocated resource instance. This means that when the smart pointer goes out of scope, as seen in the createSmartResource function, it automatically invokes the destructor for the resource object. Consequently, the dynamically allocated memory is released without the need for explicit deallocation, thus preventing memory leaks. This automated memory management not only simplifies our code, but also enhances its safety by ensuring that resources are properly cleaned up even in the case of exceptions. The design leverages the benefits of dynamic allocation while mitigating the risks associated with manual memory management, thereby promoting better coding practices in C++. The displayed bar chart titled Key Concepts in Object Lifetime Management in C++ quantifies the relative emphasis placed on 5 concepts: automatic objects 30%, resource management 25%, memory leaks 20%, smart pointers 15%, and destructor usage 10%. The bars descend steadily from left to right, indicating a clear prioritization. Automatic object lifetimes and broader resource management together account for more than half of the emphasis, 30% plus 25% equals 55%, which suggests the lesson's primary focus should be on understanding scope-bound objects and how resources are acquired and released. Memory leaks remain a substantial concern at 20%, highlighting the practical risks when resource release is mishandled. Smart pointers, while shown at 15%, are presented as a significant but secondary mitigation strategy that supports safer heap management. Their lower percentage reflects that they are a tool to apply after mastering the fundamentals. Destructor usage appears at 10%, underlining that while correct destructor implementation is essential, it is one part of a broader strategy that includes scope management, RAII, and using higher-level abstractions. The annotated percentages on each bar make comparisons immediate, and the y-axis labeled importance % shows these values as a relative allocation of attention, guiding you to prioritize learning automatic object lifetime and general resource management first, then address common failure modes, memory leaks, and supporting techniques, smart pointers, proper destructor design. As C++ programmers, we focus heavily on resource management. Understanding lifetimes gives you a powerful tool to write more efficient and stable applications. Always keep in mind that automatic objects are destructed at the end of their scope, and it's essential to ensure that resources are properly released when they're no longer needed. We have explored how to manage resource lifetimes using automatic variables, destructors, and the concept of RAII, resource acquisition, is initialization. Moving forward, we will also touch upon the implications of object copying and how it can affect lifetime management. Understanding these concepts will help you prevent bugs and ensure that your C++ applications are robust and maintainable. If you master the principles of object lifetime management, you'll be well equipped to tackle many challenges that arise while programming in C++, such as memory leaks, dangling pointers, and performance issues. As we wrap up this lesson on object lifetime management, remember that with great power comes great responsibility. Keeping track of object lifetimes is not just about making sure your application runs well today, but also about ensuring it remains stable and efficient going forward. Practice these principles regularly, and you'll develop a deep understanding of resource management that will serve you well in your programming journey. Thank you for joining me, and see you next time as we continue to explore the amazing world of C++. Resource management in C++ is crucial, especially when a class is designed to explicitly handle resources like memory, file handles, or network connections. The default generated special functions provided by C++ often do not meet the unique needs of such classes. Today, we will delve into effective resource management strategies and highlight why you need to customize these special functions for your classes. So far, we learned about the importance of object lifetime management in C++, emphasizing the roles of automatic objects and destructors in preventing memory leaks. We explored how automatic objects are destroyed at the end of their scope and the necessity of proper resource management when using dynamic memory. Additionally, we discussed smart pointers as a modern solution to enhance memory safety and reduce the complexity of manual memory management. Understanding these principles is crucial for writing efficient and stable applications in C++. Now we will talk about effective resource management by focusing on the implications of user-defined constructors, destructors, copying, and assignment operations. The displayed pie chart titled Effective Resource Management Strategies in C++ quantifies the relative emphasis placed on 5 key areas: custom constructors 25%, destructors 20%, copy semantics 20%, move semantics 15%, and smart pointers 20%. From this breakdown, we can draw several practical conclusions. The largest slice for custom constructors, 25%, highlights that correctly acquiring resources at construction is the single most emphasized practice. Destructors and copy semantics together account for 40%, underlining that releasing resources and defining correct deep copy behavior remain central to correctness. Smart pointers occupy a full 20%, indicating strong adoption of RAII abstractions to simplify ownership and prevent leaks. Move semantics at 15% represent an important, though slightly smaller, optimization-focused area that complements copying by enabling efficient transfer of resources. Overall, the chart suggests a balanced strategy where designing robust constructors and destructors and implementing correct copy behavior are primary responsibilities, while smart pointers and move semantics are essential tools that reduce manual errors and improve performance when applied appropriately. Now let's implement a class that manages a dynamically allocated array. The dynamic array class begins with a constructor that takes a size parameter, which specifies the amount of memory to allocate for an array of integers. Inside the constructor, we allocate memory using the new operator and store the size of the array in a member variable. This ensures that we can manage our resources effectively and know how much memory we have allocated. Next, we define a destructor that releases the allocated memory using the delete operator. This is crucial for preventing memory leaks when our objects go out of scope. However, managing dynamic memory involves more than just allocation and deallocation. We must also handle the copying of objects with care. To do this, we need to implement a copy constructor that performs a deep copy of the array. This constructor copies the size and allocates new memory, ensuring that each dynamic array instance manages its own separate array. Additionally, we implement a copy assignment operator that first checks for self-assignment, releases any existing resources, and then performs a deep copy just like the copy constructor. This careful management of constructor, destructor, and assignment ensures that our class adheres to good resource management practices. Now let's take a look at how shallow copying can lead to problems in our dynamic array class. In the main function, we first create an instance of dynamic array called array1 with a size of 10. Next, we attempt to copy this instance into array2 using the assignment syntax. At this point, a shallow copy occurs, meaning array2 shares the same pointer to the dynamically allocated memory as array1. This leads to a critical issue. When array2 goes out of scope at the end of the function, its destructor is called, which deallocates the memory pointed to by data. Consequently, array1 is left with a dangling pointer that references memory that has already been freed, causing undefined behavior when it is eventually destroyed. To mitigate such risks, we need to construct our own copy constructor and copy assignment operator to implement proper deep copying, ensuring each instance manages its own separate resources and prevents memory issues. Now let's implement a correct version of the dynamic array class that safely manages resource copying. This class includes a constructor that dynamically allocates memory for an array of integers, ensuring that memory is properly allocated when an instance is created. Next, we define a copy constructor, which is essential for creating a new instance of dynamic array that contains a copy of the original array, rather than sharing the same memory. This constructor performs a deep copy by allocating new memory and copying the contents from the source array, effectively preventing issues like dangling pointers that occur with shallow copies. Following that, we implement a destructor to handle the deallocation of memory when a dynamic array instance goes out of scope. This destructor ensures that we free up the allocated memory, thus preventing memory leaks. Additionally, we introduce a copy assignment operator that first checks for self-assignment to ensure safety. If the instance is not self-assigning, it releases any current memory it holds, allocates new memory, and copies the array contents just like the copy constructor. This operator is crucial for proper assignment behavior, maintaining memory integrity and preventing leaks in the process. By implementing these features, we achieve robust resource management for the dynamic array class. Now let's take a look at how we can use our modified dynamic array class to safely manage resources during object assignment and initialization. In this example, we start by creating an instance of dynamic array, named array1 with a size of 10. Next, we demonstrate the functionality of the copy constructor by creating a second instance, array2, which is initialized as a copy of array1. This means array2 will have its own separate memory, preventing any issues related to shallow copying. Following this, we introduce another instance called array3, initialized with a size of 5. To showcase the copy assignment operator, we assign array1 to array3. Since we defined our own copy assignment operator, this operation will safely handle the existing memory of array3 and ensure it gets a new, independent copy of array1's data. As a result, both array2 and array3 maintain their integrity and manage their memory without interference, demonstrating effective resource management through proper copying and assignment in C++. Now let's implement the move constructor and move assignment operator for the dynamic array class. The move constructor is designed to transfer ownership of resources from a temporary object, indicated by dynamic array and an other, to a new instance rather than making a copy. We accomplish this by assigning the pointer of the other object's data to our new object's data member, effectively stealing the resource. Next, we set the other object's pointer to nulpter, ensuring that the moved from object remains in a valid state and preventing double deletion during destruction. Similarly, we craft the move assignment operator to handle cases where an existing object might be assigned a new resource. This operator first checks for self-assignment, ensuring that the object isn't trying to move from itself. It deletes any existing resource held by the current object to release that memory before stealing the resource from the other object. By setting other's data pointer to nulpter, we again prevent memory issues stemming from attempts to delete the same resource twice. Both the move constructor and the move assignment operator use the no-except qualifier, indicating that these operations are guaranteed not to throw exceptions, which is essential for the stability of container classes that rely on these mechanisms for performance optimization. Now let's implement the following example that demonstrates the use of move semantics for efficient resource management in our dynamic array class. In the main function, we first create an instance of dynamic array named array1 with a size of 10. This allocates the memory needed to hold the array, and we see a message indicating successful allocation. Next, we utilize std, move, to transfer the resources from array1 to array2. This transforms array1 into an R value, allowing the move constructor to be called. The move constructor takes over the ownership of the memory from array1 and sets array1 to a safe state by nulling its pointer, thus preventing double deletion when both instances go out of scope. Following this, we create array3 with a size of 5 and again employ move semantics using std, move, to assign array2 to array3. This process uses the move assignment operator that takes the resources from array2, leaving it in a valid state while allowing array3 to manage the memory. This efficient transfer eliminates the performance overhead associated with deep copying, demonstrating the power of move semantics in managing resources effectively. Now that we've covered resource management strategies from copy to move semantics, it's essential to note why this is vital for avoiding memory leaks and ensuring resource integrity. In real-world applications, managing resources effectively is key. Failure to define the necessary constructors, destructors, and assignment operators can lead to resource leaks, dangling pointers, and severe performance hits. Effective resource management significantly enhances the stability of your C++ applications. It ensures that your program does not unintentionally keep hold of memory that is no longer required or, worse, attempt to access invalid pointers. The careful definition and implementation of special member functions like copy constructors and assignment operators allow for controlled resource management. As we conclude this discussion, remember that resource management in C++ goes beyond just writing constructors and destructors. It requires careful consideration of how your objects handle the resources they own. Following the principles of the rule of 3 or the rule of 5 will empower you to write more robust, efficient, and safe C++ code. By mastering these strategies, you ensure that your C++ applications can not only avoid common pitfalls associated with resource management, but also leverage the strengths of the language for optimal performance. Happy coding, and see you in the next lesson as we continue exploring the powerful features of C++ and resource management. Resource management in C++ is a crucial topic that every developer must grasp to write efficient and safe applications. It deals with how a program handles various resources such as memory, file handles, and other system resources. Today, we'll dive deeper into advanced resource management techniques, focusing on explicit resource management in classes and how default-generated special functions may not meet our needs. So far, we learned about the significance of effective resource management in C++, focusing on the need for user-defined constructors, destructors, and assignment operators to handle dynamic memory safely. We explored the pitfalls of default copying behaviors, such as shallow copies leading to dangling pointers, and how implementing move semantics can enhance performance by transferring resource ownership efficiently. Additionally, we emphasized the importance of the rule of 3 or rule of 5 in designing classes that manage resources responsibly. These strategies are essential for writing robust and efficient C++ applications, preventing memory leaks and ensuring resource integrity. Now we will talk about more advanced techniques, including custom resource management strategies and best practices in C++. Now let's see how we can implement a class called buffer that manages dynamic arrays responsibly. The class defines a constructor that dynamically allocates an array of integers, and it ensures that resources are released properly using a destructor that deletes the allocated memory. Next, we will write a copy constructor for the buffer class, which performs a deep copy of another buffer object. This means that it allocates new memory for the copied data instead of merely copying the pointer, ensuring that each buffer instance maintains its own separate copy of the array. Additionally, we must implement the copy assignment operator, which first checks for self-assignment before freeing existing memory, updating the size, and copying the data from the source buffer. To enhance performance further, we also define move semantics. The move constructor and move assignment operator transfer ownership of resources efficiently without unnecessary duplication, nullifying the original pointers in the source object to prevent double deletion. Through these carefully defined constructors and operators, we can ensure that our buffer class handles dynamic memory safely and efficiently, adhering to resource management best practices in C++. Now let's take a look at the implementation of a resource class that adheres to the rule of 5, ensuring robust resource management. This class manages dynamic memory through an integer pointer and a size attribute. First, we define a constructor that initializes the capacity and allocates memory for items, allowing dynamic integer storage. The destructor is essential as it ensures that the allocated memory is released when the object is destroyed, preventing memory leaks. Next, we implement the copy constructor, which facilitates deep copying by allocating new memory for items and copying data from the source object. This ensures that each resource instance maintains its own copy of the data. In the copy assignment operator, we first check for self-assignment to prevent accidental resource mishandling. If they are not the same, we free the existing resource, allocate new memory, and copy over the content, sustaining the integrity of the resource management. Moving on, the move constructor and move assignment operator optimize the transfer of resources by utilizing R-value references, efficiently transferring ownership and nullifying the original pointers in the moved from object, which is crucial for performance in C++. This correct management of resources empowers the resource class, making it versatile and safe for dynamic memory usage, highlighting the importance of implementing all 5 special member functions when custom resource management is required. The accompanying pie chart titled Resource Management in C++ shows 4 categories with their relative shares: dynamic memory 60%, file handles 25%, custom strategies 10%, and smart pointers 5%. The largest portion, dynamic memory at 60%, indicates that manual memory allocation and deallocation are the most prominent resource concerns in this depiction. File handles make up a significant secondary share at 25%, calling attention to I/O-related resource management as another common area of focus. Custom strategies represent 10%, reflecting tailored or domain-specific approaches, while smart pointers account for only 5%, suggesting they are comparatively less represented in this distribution. From these proportions, one can conclude that techniques addressing raw dynamic memory and explicit ownership transfer, deep copies, move semantics, careful destructors, address the bulk of cases shown, while file handle management and custom strategies also require deliberate handling. The relatively small slice for smart pointers highlights that, although valuable, automatic pointer abstractions are shown here as a smaller portion of the overall resource management landscape, which motivates why we continue to discuss both manual and automated strategies. Now let's see how we can implement smart pointers in C++ using the example of std, unique PTR. This code demonstrates the use of std, unique PTR, which manages ownership of dynamically allocated objects automatically. The class example is defined with a constructor that outputs a message when an object is created, and a destructor that does the same when the object is destroyed. Next, we will write a function called createExample. Inside this function, we declare a std, unique PTR called example_PTR, and initialize it with an instance of example using std, makeUnique. This line of code not only creates the object but also ensures that example_PTR takes sole ownership of the example instance. As the function reaches its end and example_PTR goes out of scope, the example object is automatically deallocated, triggering the destructor and thus eliminating any risk of memory leaks. This automatic resource management aspect of std, unique PTR, highlights its efficiency and suitability for scenarios requiring clear ownership semantics. Next, we will write the following example to illustrate how std, shared PTR, can manage shared ownership of resources in C++. In our code, we define a simple class, sharedExample, that outputs messages when instances are created and destroyed. This helps us observe the life cycle of the object. In the sharedExample function, we begin by creating a std, shared PTR named sharedPTR1, which is initialized with a new instance of sharedExample. This pointer maintains ownership of the sharedExample object. Now let's see how we can implement shared ownership by introducing another shared PTR, sharedPTR2. This pointer takes on the same object as shared PTR, effectively sharing ownership of the sharedExample instance. When shared PTR2 goes out of scope, the resource is not immediately released, demonstrating the essence of shared ownership. As long as one shared PTR exists, the underlying resource remains valid. This provides flexibility in managing the resource's lifecycle, but it also entails some memory overhead due to reference count maintenance. Understanding this mechanism is key to leveraging std, shared PTR, effectively in C++ for safe and efficient resource management. Now let's take a look at an example demonstrating how to manage circular dependencies using shared pointers. In the circular dependency class, we define a member variable that is a shared pointer to another instance of circular dependency. The constructor and destructor print messages to indicate when instances are created and destroyed, helping us visualize their life cycle. Next, we implement a function called circularExample, where we create two shared pointers, first and second, both pointing to separate instances of circular dependency. Here, we establish a circular reference by assigning each object's shared pointer member to point to the other. This creates a problematic cycle. Despite both objects being referenced, the reference count never drops to 0, leading to a memory leak. To break this cycle, we could use std, weak PTR, for one of the pointers, allowing us to observe the object without contributing to its reference count. This would permit the objects to be destroyed when they go out of scope, effectively managing the lifetimes and preventing the memory leak caused by circular dependencies. Thus, this example highlights the importance of smart pointers in resource management, particularly in dealing with complex ownership scenarios. It's important to always choose the right type of smart pointer based on your resource management needs. std, unique PTR for sole ownership, std, shared PTR for shared ownership, and std, weak PTR to break cycles are excellent strategies. As we wrap up, remember that resource management in C++ is a complex but vital part of writing robust programs. Avoiding pitfalls such as memory leaks and dangling pointers is essential for application stability and performance. As you develop your classes, pay attention to the principles we've discussed. the rule of 5, explicit resource management through constructors and destructors, and leveraging smart pointers for automatic management. Using these techniques will elevate your code quality and provide a greater understanding of how C++ effectively manages resources under the hood. Happy coding! Now let's take a look at how we can implement a class to manage a dynamic array. The array class is designed to handle a resource, a dynamically allocated array of integers. In the constructor, we initialize the array by allocating memory based on the provided length. The destructor ensures that this allocated memory is properly released to prevent memory leaks when the object goes out of scope. Next, we have the copy constructor, which takes another array object as a parameter to create a copy. This involves allocating new memory for the data and copying the contents from the original array. Similarly, the copy assignment operator checks for self-assignment, cleans up any existing memory, and then allocates new memory while copying from the provided object. These implementations ensure that we can safely copy objects, but they come with performance costs due to memory allocations. To address this, we'll later enhance our class to support move semantics, allowing us to transfer ownership of resources without unnecessary copies. This sets the stage for optimizing our resource management, allowing for improved efficiency and performance in our C++ applications. The figure titled Key Concepts of Move Semantics in C++ shows 4 categories on the x-axis: resource management, move semantics, rule of 5, and smart pointers, with corresponding importance percentages on the y-axis: 40%, 30%, 20%, and 10% respectively. The clear pattern is that resource management occupies the largest single share, 40%, indicating that foundational skills in correctly acquiring, owning, and releasing resources are the primary concern. Move semantics itself is the next largest at 30%, highlighting that transferring ownership to avoid copies is a major, but secondary, focus built on top of resource management. The rule of 5 at 20% reflects the practical requirement to implement the full set of special member functions when managing ownership, while smart pointers at 10% represent important supporting techniques that help manage lifetime and ownership, but are shown as a smaller, complementary portion of the overall emphasis. From these proportions, we can conclude that a practical learning path is to prioritize robust resource management practices first, then concentrate on move semantics to optimize transfers, followed by understanding the rule of 5 for correctness, and finally incorporate smart pointers as tools that simplify many ownership patterns. Now let's see how we can implement move semantics in our array class to enhance performance. We begin by defining a move constructor that takes an R-value reference to an array object. This special constructor initializes the new object by transferring the data pointer and the length from the other object while leaving the other in a valid state by setting its data pointer to nullter and its length to 0. This ensures that when the destructor of the other object is invoked, it doesn't mistakenly attempt to free memory that has already been transferred. Next, we implement the move assignment operator, which is crucial for assigning one array object to another without unnecessary overhead. It first checks for self-assignment to prevent issues, then deletes any existing resource before stealing the data from other. Just like in the move constructor, it sets other data to nullter and other length to 0 to maintain a safe state for the move from object. By incorporating these two operations, our array class not only avoids costly deep copies, but also simplifies memory management, letting us leverage the full benefits of move semantics in our applications. Now let's see how we can implement move semantics in practice with our array class. The getArray function illustrates the concept of return value optimization, RVO, and move semantics by returning a temporary array object. This function simplifies the process of creating an array without the overhead of copying it when it returns. Instead, the main function demonstrates how the temporary object can be efficiently transferred to myArray, allowing us to utilize move semantics. Then when we want to assign myArray to another array, we use the std move function, which explicitly indicates that we wish to transfer ownership of the resources from myArray to another array. This is where the move constructor comes into play, transferring the data pointer and the length of the array to another array while leaving myArray in a valid but unspecified state. By doing so, we've optimized resource management, illustrating the efficiency gains of move semantics and demonstrating how we can write more performant C++ code that minimizes unnecessary copying of resources. Now let's implement the move constructor for our array class, which is crucial for enabling move semantics. This constructor takes an R-value reference to another array object, allowing it to steal the resources held by the original object. By marking this constructor with the noexcept specifier, we inform the compiler that this operation will not throw exceptions, which enhances performance through optimization opportunities in standard containers. In the implementation, we initialize the new object's data pointer with the other object's data and set its length to match. Crucially, we then set the other object's data pointer to nulpter, which ensures that when the destructor of other is called, it does not attempt to delete the same memory that we've just taken control of. This leaves other in a safe state, preventing potential double deletions or undefined behavior. This move constructor not only eliminates the overhead of copying resources, but also simplifies memory management. By leveraging move semantics, we significantly enhance the efficiency of our array class, making it a powerful tool for modern C++ programming. Now let's take a look at how we can implement the rule of 5 in our array class to ensure efficient resource management. This class includes a constructor that allocates memory for a dynamic array and a destructor that releases this memory when the object is no longer needed, thereby preventing memory leaks. Next, we will define a copy constructor that creates a new array object as a deep copy of another existing object. This constructor initializes the new array while ensuring it has its own independent memory space. Additionally, we'll include a copy assignment operator that checks for self-assignment and properly handles resource cleanup by deleting existing data before allocating new memory and copying the contents from the source object. Now let's implement the move constructor and move assignment operator to leverage move semantics. The move constructor allows us to transfer ownership of the dynamic array from a temporary object, leaving the original in a safe state by nullifying its pointer. Similarly, the move assignment operator first releases its current resources, then takes over the memory from the provided object, ensuring efficient transfers without unnecessary allocations. By incorporating these features, we adhere to the rule of 5 and enhance the performance of our class. Now let's implement the following practical example of using move semantics with a standard library container, specifically std vector. The code begins by including the vector header necessary for utilizing the std vector container. In the main function, we declare a vector named arrays designed to hold objects of the array class we previously discussed. Next, we utilize the pushback method to add a new array object to the vector. Here is where move semantics come into play. By passing a temporary array created with a size of 10, we avoid the overhead of copying this object into the vector. Instead, C++ efficiently moves the resources of the temporary array directly into the vector's memory space. This action accelerates execution since it eliminates the need for additional memory allocation and copying operations. However, it's important to remember that after moving an object, the original object is left in a valid but unspecified state, which means it cannot be reliably used without reinitialization. This feature showcases how move semantics can significantly enhance performance, especially when dealing with containers in C++. Now, while move semantics can be incredibly powerful, it's essential to remember that not all classes should adopt move semantics. If your class manages non-heap resources like file handles or other system resources, moving may not apply. In such cases, the semantics of copying remain important, as resources should be managed in accordance with how they should be shared or passed around. For instance, if you have a class that manages a file handle, a move operation might not make sense because the file handle will likely be invalidated when moved. In instances like these, consider carefully whether your class needs both move and copy capabilities, or if you should provide either one of them. Let's wrap up our discussion on move semantics. Understanding move semantics in C++ enables you to create more efficient and robust applications, especially in performance-critical scenarios where copying data could lead to significant slowdowns. With the right use of move constructors, assignment operators, and proper management of resources, we can significantly reduce overhead costs. We've explored how move semantics works using code examples, the importance of adhering to the rule of 5, ensuring no-throw guarantees, and practical applications with SDL containers. Dive into your code and start incorporating move semantics to see the efficiency gains for yourself. Remember, with great power comes great responsibility, so ensure your resources are managed appropriately. Thank you for joining today's session. Keep practicing, keep experimenting, and as always, happy coding. Now let's take a look at the myArray class, which helps illustrate the rule of 3 in C++. This class manages a dynamic array of integers and includes a user-defined constructor, destructor, and copy assignment operator to ensure proper resource management. In the constructor, memory for the array is allocated using the new operator, taking into account the size passed as an argument. This dynamic allocation is crucial for handling arrays whose size might not be known at compile time. Next, we implement the destructor, which is a vital component. It ensures that when an object of myArray goes out of scope, the memory allocated for the array is properly released using delete, thus preventing memory leaks. Now let's see how we can implement the copy constructor. This constructor allows an existing myArray object to be copied into a new instance, ensuring a deep copy by allocating new memory and copying each element. This approach prevents multiple objects from unintentionally sharing the same memory. Lastly, the copy assignment operator manages the assignment of one object to another while handling self-assignment and ensuring that memory is cleaned up before reallocation, reinforcing the importance of safe memory management in C++. Next, we will implement the copy constructor for our myArray class. This constructor is responsible for creating a new object that is a copy of an existing one. To achieve this, we begin by initializing the size member with the size of the other object we are copying from. Now let's see how we handle memory allocation. We allocate a new block of memory for the R member, which will ensure that each myArray instance manages its own separate array. This is crucial because, by default, if we simply copy the pointer, both objects would refer to the same memory address, leading to potential issues when one object is destroyed or modified. Next, we iterate through the other objects R, copying each element into our newly allocated memory. This step guarantees that the new object has its own distinct copy of the array's contents, preventing shared ownership problems. By following this deep copy approach, we ensure that our myArray class behaves well in terms of memory management and maintains the integrity of the data when multiple instances exist. The figure titled Comparison of Importance of Key C++ Concepts for Memory Management displays a grouped bar chart with 3 categories along the x-axis: destructor, copy constructor, and copy assignment. For each category there are 2 bars, one for efficiency and one for resource management, with the y-axis showing importance % and a legend identifying the 2 measures. The numeric values depicted are efficiency equals destructor, 30%, copy constructor, 50%, copy assignment, 50%, and resource management equals destructor, 40%, copy constructor, 30%, copy assignment, 30%. Key patterns visible are both copy-related operations, copy constructor and copy assignment, are shown as having the highest importance for efficiency at 50%, which is 20 percentage points higher than the destructor's efficiency at 30%. Conversely, the destructor has the highest score for resource management at 40%, 10 percentage points above the copy operation's resource management scores of 30% each. From these values, we can conclude the visualization emphasizes that implementing correct copy behavior is presented as most critical for performance aspects, while the destructor is highlighted as the most critical for safely managing and releasing resources. The juxtaposition of the 2 measures underscores the complementary roles of these 3 special member functions. Copy operations matter most for runtime efficiency, the destructor matters most for resource cleanup, and all 3 together balance correctness and performance. Now let's see how we can implement the copy assignment operator in our myArray class. The primary purpose of this operator is to allow an existing object to be assigned the values of another object of the same type after both have been constructed, ensuring proper management of the resources involved. In our implementation, the first thing we do is check for self-assignment by comparing the address of the current object with the address of the object being assigned. This step is crucial because if an object tries to assign itself, we need to avoid unnecessary memory operations that could lead to data loss or corruption. If the objects are not the same, we proceed to safely release any memory that the current object's array may be holding, thus preventing memory leaks. Once the existing memory is cleared, we update the size of the current object to match the size of the other object and allocate new memory for its array. Finally, we copy each element from the source object's array to the newly allocated array. By returning a reference to the current object at the end, we facilitate the chaining of assignment operations, making our class more intuitive to use. This careful implementation ensures that we manage resources effectively while adhering to the rule of three. Now let's take a look at how we can implement the rule of three in our myArray class, which effectively manages a dynamic array. First, we define a constructor that initializes the size of the array and allocates memory for it using new. This code snippet highlights the importance of resource management right from object creation. Next, we implement the copy constructor, which is crucial for creating a new myArray object as a copy of an existing one. It allocates new memory and performs a deep copy of the elements, ensuring that each instance manages its resources independently and does not lead to unwanted memory conflicts. Following this, we write the copy assignment operator, which allows one object to be assigned to another after both have already been constructed. Here we include a check for self-assignment and carefully manage memory by first deleting any existing memory before reallocating and copying the new data. Finally, we implement the destructor, which is essential to avoid memory leaks by deallocating the memory allocated for the array when the object goes out of scope. This comprehensive approach ensures that the myArray class adheres to the rule of three, providing effective and safe resource management throughout its lifecycle. As we conclude this lesson, it's essential to remember that learning how to manage object lifetimes effectively is foundational for writing robust C++ programs. Grasping the concepts of copying and moving objects can significantly improve performance and help you avoid common pitfalls associated with resource management. In our next lesson, we will explore move semantics further and discuss how it complements the rule of three, allowing for even more efficient object management in contemporary C++ code. Get ready to unlock new potentials within your programming skills, where you'll learn to optimize memory use and streamline your applications. See you then. Memory management in C++ is one of the language's strengths, but it also introduces a level of complexity that can challenge even seasoned developers. At its core, C++ provides robust control over the lifetime and scope of objects, and mastering this control can lead to more efficient and effective code. Today, we're going to explore the fundamentals of memory management in C++, focusing on how to handle objects' lifetimes, the importance of resource management, and the strategies you can implement to prevent common pitfalls such as memory leaks and dangling pointers. So far, we learned about the rule of three in C++, which includes the destructor, copy constructor, and copy assignment operator, emphasizing their importance in resource management. We discussed how a destructor cleans up dynamically allocated memory to prevent leaks, while a copy constructor and copy assignment operator facilitate deep copies to manage object ownership correctly. Implementing these principles ensures robust handling of objects and memory within C++ applications. In the next lesson, we will delve into move semantics, enhancing our understanding of efficient resource management. The accompanying bar chart compares four key C++ memory management concepts: destructor, copy constructor, copy assignment, and smart pointers, by plotting two metrics for each: importance % and difficulty %. From the plotted values, smart pointers stand out with the highest reported importance, 80%, while having the lowest difficulty, 30%, indicating that they are both central to modern practices and relatively accessible to use. The destructor is also shown as highly important, 75%, with low to moderate difficulty, 40%, underscoring the continued need for explicit cleanup logic or RAII-style handling. Copy constructor and copy assignment share the same importance level, 60%, but they are slightly more difficult, 50% and 45% respectively, than destructors. The copy constructor is the most difficult of the two, suggesting that correctly implementing copying semantics, deep copies, ownership transfer rules is a common pain point. The chart's axes label the horizontal categories as the key concepts and the vertical axis as percentage. The legend distinguishes importance, sky blue, and difficulty, salmon. Taken together, these patterns reinforce the lesson's emphasis. Destructors and smart pointers are central to safe resource management, while copy semantics require careful attention because they are moderately difficult even when considered important. Now let's see how memory can be allocated on the heap using a simple example. In this code, we define a function that demonstrates heap memory allocation by creating an integer pointer named num. We utilize the new keyword to allocate memory on the heap, initializing it with the value 10. This means that the integer does not just exist within the scope of the function, but persists until explicitly deleted, allowing for flexibility in memory use. After displaying the value pointed to by num, we must remember to free the allocated memory to avoid memory leaks. This is done using the delete keyword, which deallocates the memory previously assigned to num. It's crucial to ensure that delete is called, as failing to do so would leave memory allocated without a reference, ultimately consuming system resources unnecessarily. This example encapsulates the importance of careful memory management in C++, highlighting that while the heap offers control and persistence, it also requires diligent attention to free up resources when they are no longer needed. Next, let's take a look at how we can work with dynamically allocated memory in C++ by examining the functions defined in our code example. The createNumber function is responsible for allocating an integer on the heap and returning a pointer to it. This demonstrates the concept of heap memory allocation, where memory persists past the end of the scope it was created in, unlike stack memory, which is automatically cleaned up. Moving to the example function, we first call createNumber to acquire a pointer to the newly allocated integer. Subsequently, we delete this pointer to free the associated memory and prevent leaks. However, it's crucial to understand that after deletion, the pointer becomes dangling. It still retains the address of the deleted memory but cannot be safely accessed. As a protective measure, we then set the pointer to nulpter. This step is essential as it prevents accidental dereferencing of a dangling pointer, demonstrating a fundamental principle of safe memory management in C++. By employing this strategy, we ensure that our program adheres to best practices for dynamic memory management, effectively mitigating risks associated with memory misuse. Now let's take a look at a class that effectively demonstrates the principles of memory management, focusing on dynamic allocation and proper resource cleanup. This myClass is designed to manage an integer pointer, data, which is initialized through the constructor. When we create an instance of myClass, it allocates memory on the heap for this integer using the new keyword, initializing it with the value provided as an argument. The destructor plays a crucial role in this class. When a myClass instance goes out of scope, the destructor is automatically called, freeing the memory allocated to data with the delete statement. This ensures that we prevent memory leaks by properly releasing resources that are no longer needed. Additionally, the class includes a public method, display, which allows us to access and output the value pointed to by data. With this setup, the myClass implementation adheres to the rule of 3 by encompassing allocation, deallocation, and ensuring proper management of dynamically allocated memory within a class context, allowing for safe and efficient C++ programming practices. Now let's take a look at a practical implementation of resource management in C++ using a file handler class. The file handler class we are going to explore demonstrates the importance of managing resources such as file handles through the use of constructors and destructors. In this class, we begin by including the fstream library, which provides the functionality to work with files. The file handler constructor accepts a file name as a parameter and opens the file in read-write mode while also allowing for appending. By opening the file during the object's construction, we ensure that the file is ready for any operations we may wish to perform. The key component of this class is the destructor, defined with a tilde before the class name. This destructor is invoked automatically when an object of file handler goes out of scope. Inside the destructor, we check if the file is still open. If it is, we close it. This is crucial as it prevents potential resource leaks or file contention issues, demonstrating the principle of cleaning up resources effectively. The design of this class not only encapsulates file handling logic, but also highlights the fundamental role destructors play in C++ memory management. Next, let's take a look at the deepcopy class, which effectively demonstrates the principles of the copy constructor and memory management. This class is designed to manage a dynamically allocated integer, highlighting how to safely copy objects to avoid issues commonly associated with shallow copies. The constructor initializes the data member by allocating memory on the heap and assigning it a value. This is crucial since it ensures that the object owns its resource. Now, let's focus on the copy constructor. When an object of deep copy is copied, this constructor is invoked, which performs a deep copy by allocating new memory for data and copying the value from the source object. This ensures that each deep copy instance is independent, preventing problems like double deletion when both the original and copy go out of scope. In conclusion, this implementation adheres to the rule of 3 in C++, showcasing the critical role of a properly defined copy constructor in managing dynamic memory. Understanding these concepts is essential for creating robust and reliable C++ applications, mitigating common risks associated with memory management. Now let's take a look at implementing the copy assignment operator for our deep copy class, a critical component in memory management. This operator allows us to correctly assign one instance of deep copy to another, ensuring that resources are managed appropriately without leading to memory leaks or dangling pointers. The operator begins with a self-assignment check, verifying if the current object is the same as the one being assigned to. If they are different, we first delete the existing resource that the current object points to, which prevents memory leaks that could arise from losing that reference. Following this, we create a deep copy of the resource from the source object. This involves allocating new memory for the data and copying the value from the source object's data, ensuring our new object has its own independent copy. Finally, we return a reference to the current object, allowing for assignment chaining. This careful management with a self-assignment check and deep copying reinforces the importance of the rule of 3 in C++, maintaining robust and independent instances of our class while preventing potential memory mismanagement. Now let's take a look at how we can leverage smart pointers, specifically STD, unique PTR, in our code to manage dynamic memory automatically. In the example, we define a function called useSmartPointer where we create a unique PTR that takes ownership of an integer allocated on the heap. This is initiated with new int 30, which allocates memory for an integer initialized to 30. The beauty of using STD, unique PTR, lies in its automatic memory management. Once the useSmartPointer function exits, the smart PTR will automatically release the memory it owns without requiring an explicit delete statement. This minimizes the risk of memory leaks, a common pitfall when dealing with manual memory management, as we no longer need to remember to free the allocated memory. Furthermore, by using std count, we can access the value pointing to smart PTR and output it to the console. This integration of smart pointers exemplifies modern C++ practices, showcasing how they simplify resource management while ensuring safe and efficient memory allocation. Through our tutorial today, we've underscored the significance of managing resources and memory within C++. Understanding constructors, destructors, copy constructors, and smart pointers forms a solid foundation for writing effective and efficient C++ code. As we continue to explore these topics, our next session will delve deeper into move semantics, allowing you to enhance your resource management skills and unlock even greater efficiency in your applications. Remember, mastering memory management is not just about preventing leaks. It's about creating high-performance, robust applications that leverage C++'s extensive capabilities. Keep practicing these principles, and you'll be well on your way to becoming a proficient C++ developer. Until next time, happy coding. Understanding object lifetime management in C++ is crucial for effective memory management. In this session, we'll delve into how automatic objects are destructed at the end of their scope and the implications it has for our coding practices. So far, we learned about the complexities of memory management in C++ and the importance of the rule of 3, which includes the destructor, copy constructor, and copy assignment operator. We explored how to properly manage object lifetimes, dynamic memory allocation, and prevent issues like memory leaks and dangling pointers. Additionally, we introduced smart pointers as a modern solution for automatic memory management, enhancing the robustness of our applications. Now we will cover the concept of object lifetime management to solidify our understanding of how objects are created, used, and destroyed in C++. Now let's take a look at how automatic objects function in C++. The code defines a simple class, object, which has a constructor and a destructor. The constructor outputs a message when an object is created, while the destructor does the same when it's destroyed. The createObject function demonstrates the concept of automatic objects by declaring an instance of object named obj within its scope. As soon as the createObject function is entered, the constructor of obj is called, leading to the output that the object has been created. Once the function is exited, obj goes out of scope, and the destructor is automatically invoked, signaling that the object has been destroyed. This behavior exemplifies the core principle of C++ memory management. Resources are automatically managed based on scope. When the main function calls createObject, you can observe this lifecycle as the program flows through its execution, cementing the idea of automatic object management in C++ and its efficiency in preventing memory-related issues. Now let's take a look at how we manage object lifetimes with automatic variables in C++. This example introduces two classes, first and second, each with a constructor and destructor that output messages to the console, allowing us to track the creation and destruction of objects. When we call the function, instances of both classes are created in the local scope. Upon exiting the function, the destructors are invoked in reverse order of construction, meaning that second is destructed before first. This ordering is crucial to understand, particularly if second relied on first while they were alive. Such dependency relationships highlight the importance of knowing how object lifetimes overlap and the possible ramifications of accessing an object that has already been destroyed. By observing how this mechanism works, we gain valuable insights into resource management in C++. Understanding this behavior helps us avoid potential pitfalls, such as accessing invalid resources after an object has been destructed, ensuring our code remains robust and reliable during execution. This foundational knowledge is vital as we delve deeper into C++ memory management practices. Now let's see how we can implement dynamic object creation and destruction in C++. In this example, we define a class called dynamicObject, which has a constructor and a destructor that provide feedback when the object is created and destroyed. The constructor outputs dynamicObject created, while the destructor outputs dynamicObject destroyed, giving us insight into the object's life cycle. In the main function, we create a pointer to a dynamic object using the new keyword, which allocates memory for the object on the heap. This means that the object will exist until we explicitly free the memory, unlike automatic objects that get destroyed when they go out of scope. After possibly using the dynamic object, it is crucial to free the allocated memory using the delete keyword to prevent a memory leak, which occurs if the destructor is never called. Omitting this step would result in the memory allocated for dynamic object remaining inaccessible and unreleased. This code highlights the importance of manual memory management in C++, emphasizing the developer's responsibility to track dynamic allocations diligently. Now let's see how we can effectively manage the lifetimes of automatic and dynamic objects by looking at the holder class. This class illustrates the concept of an automatic object that contains a pointer to a dynamically allocated integer, showcasing how these two types of object management can work together. In the holder class, we allocate an integer on the heap using new within the constructor, allowing us to store a value that persists beyond the scope of the function. The constructor also outputs a message confirming the creation of the holder. When the example function exits, the holder object is automatically destructed, invoking the destructor which is responsible for releasing the dynamically allocated memory. This ensures that there are no memory leaks, as the allocated resource is freed when the automatic object goes out of scope. This interplay between automatic and dynamic memory management highlights the importance of understanding object lifetimes in C++. By wrapping dynamic allocations in automatic objects, we can streamline resource management, allowing the compiler to handle destruction while we focus on utilizing these objects effectively in our code. The figure titled Object Lifetime Management in C++ displays a bar chart of key concepts on the x-axis: automatic objects, dynamic objects, smart pointers, memory leaks, destructor calls, and their assigned importance level on the y-axis, with numeric labels shown on each bar. Automatic objects equals 40, dynamic objects equals 30, smart pointers equals 20, memory leaks equals 5, destructor calls equals 5. The most prominent bar is automatic objects at 40, indicating that automatic storage duration and scope-based destruction are emphasized as the highest priority concept. Dynamic objects at 30 is the next largest bar, underscoring that manual allocations and explicit lifetime control remain a major concern. Smart pointers appear at 20, showing they are a significant but secondary strategy, bridging manual dynamic allocation and automated cleanup. The much smaller bars for memory leaks and destructor calls, both 5, indicate these outcomes are shown as lower-level items in this ranking. Memory leaks are presented as a relatively small slice of the overall focus, implying they are consequences to avoid. An explicit destructor invocation is likewise a small, specific concern compared with broader storage duration choices. From these displayed values, we can draw practical conclusions aligned with the lesson. Prioritize designing around automatic objects and clear ownership, treat dynamic allocation carefully, adopt smart pointers to reduce manual delete calls and lower the incidence of memory leaks, and keep destructor behavior in mind as a necessary but less emphasized part of the overall management strategy. Now let's see how we can implement container classes utilizing the C++ standard template library, STL, to manage object lifetimes automatically. In the following example, we create a class called item that has a constructor and a destructor. The constructor initializes an integer member variable while printing a message indicating that the item is created. Similarly, the destructor outputs a message when the item is destroyed. Inside the main function, we create a std vector that will hold instances of item. The emplaceback function is used to add items to the vector, which invokes the constructor for each new item. This design highlights the use of automatic objects. Once the vector goes out of scope at the end of the main function, all item objects contained in the vector are destructed automatically. This not only prevents memory leaks, but also simplifies the management of object lifetimes, showcasing the elegant memory handling features of STL containers. By observing the destructor messages, we can truly appreciate the order of destruction and the robustness this automatic management provides. Now let's see how we can implement smart pointers to manage object lifetimes effectively. In the code, we define a class called smartObject, which contains a constructor and a destructor that print messages upon creation and destruction, respectively. This provides clear feedback about the object's lifecycle. Next, we utilize std, unique PTR, a smart pointer that automatically manages the memory of smartObject. By creating a unique pointer, objptr, and assigning it a dynamically allocated smartObject using std, make unique, we ensure that the object is automatically cleaned up when objptr goes out of scope at the end of the main function. This approach eliminates the need for a manual delete call, reducing the risk of memory leaks and dangling pointers. Through this implementation, we see the advantages of automatic memory management in modern C++, which enhances code safety and readability. The unique pointer takes responsibility for the object's lifecycle, demonstrating the principle of resource management inherent in smart pointers while allowing us to focus more on the logic of our applications without worrying about manual memory handling. As we wrap up our discussion on object lifetime management in C++, it's vital to remember the impact proper object lifecycle management has on the stability and performance of your applications. Using the right practices, such as leveraging automatic storage duration and employing smart pointers, can help avoid common pitfalls, such as memory leaks and dangling pointers. Remember that C++ offers a rich set of tools and practices that we can harness for effective memory management. Be diligent in utilizing automatic objects properly, understanding the destruction order, and being aware of dynamic memory's particularities to write efficient and error-free code. So in our journey today, we explored the principles surrounding object lifetime creation, destruction order, dynamic versus automatic memory management, and intelligent resource handling through modern features like smart pointers. These concepts will arm you to craft solid, efficient applications while sidestepping the memory management landmines often seen in C++. In our next lesson, we will dive into Move Semantics to further improve resource management and performance efficiency in our C++ programs. Happy coding! In this lesson, we will explore advanced resource management techniques in C++. When a class explicitly manages resources, the default-generated special functions rarely do what we would want. We'll dive deep into the intricacies of how to handle resource management effectively to avoid common pitfalls that can lead to memory leaks, improper resource handling, and other challenging bugs. So far, we learned about the significance of object lifetime management in C++, focusing on automatic and dynamic objects and their respective destruction orders. We explored the importance of the rule of three and the advantages of utilizing smart pointers to enhance memory management practices. Additionally, we discussed the role of STL containers in managing object lifetimes automatically and introduced the rule of zero for simplifying resource management. Now we will talk about the advanced techniques needed when a class takes on the responsibility of managing resources directly. Now let's take a look at how we can implement a dynamic array class that encapsulates dynamic memory management while adhering to the rule of three principles. This class begins by defining private members, an integer pointer array to hold the dynamically allocated array, and a size variable to track its size. Next, we implement a constructor that allocates the required memory based on the given size, ensuring that the array is initialized correctly. We also define a destructor that correctly deallocates this memory to prevent leaks when the dynamic array object goes out of scope. Crucially, the copy constructor is defined to create a deep copy of the array. This function allocates new memory and copies the contents of the original array, thereby preventing issues related to shallow copies. Similarly, the copy assignment operator first checks for self-assignment, releases any existing memory to avoid leaks, and then performs the deep copy. Overall, this implementation ensures that each dynamic array instance maintains its own unique resource, preventing accidental data corruption or memory leaks through proper management of copy operations. Such practices solidify the fundamentals of resource ownership in C++. Now let's modify our dynamic array class to include move semantics, enhancing how we manage resources during object transfers. The move constructor is designed to efficiently transfer the resources from an existing object, other, to a new instance. This constructor takes an R-value reference and initializes the new instances, array, and size directly from other. Crucially, it sets other array to nulpter, ensuring that the original object is left in a valid state and cannot inadvertently deallocate the memory that now belongs to the new object. Next, we will implement the move assignment operator, which serves a similar purpose. It first checks for self-assignment to prevent unnecessary work and potential errors. If the current instance is not the same as other, it releases any memory it holds before taking ownership of the resources from other. Following this, it again sets other to a default state by nullifying its array and resetting its size. These measures effectively minimize performance overhead while maintaining robust resource management, showcasing the power of move semantics in modern C++. Now let's take a look at how to effectively integrate the dynamic array class into a standard C++ vector, leveraging automatic resource management. In our example, we begin by declaring a vector of dynamic array objects. The emplaceback method is then used to directly construct dynamic array instances within the vector. This method efficiently creates objects in place, allowing us to avoid unnecessary copies. Next, we use the std move function to transfer the ownership of the first element in the vector to a new dynamic array variable named r. This invokes the move constructor we defined earlier, which efficiently transfers resources without the overhead of copying. When we move r back into the vector with the second element, the move assignment operator is called, repurposing the resources held by r into the second vector element. Finally, it's important to note that the vector manages the die and destruction of these objects automatically when they go out of scope, ensuring that there are no memory leaks or dangling pointers in this setup. This approach not only simplifies resource management, but also enhances the performance characteristics of our dynamic array operations within a container context. Now let's take a look at how we can implement a resource manager class to effectively manage multiple file resources. This class employs a vector to hold multiple instances of std ifstream, allowing centralized control over file handling. The addFile method demonstrates efficient resource management by creating an ifstream object for a specified file name and checking if the file is open. If successful, it uses std move to transfer the ownership of the file stream into the vector, which avoids unnecessary copies and enhances performance. Additionally, the readall method iterates through the vector of file handles and reads each line from the files sequentially. Inside this method, a string variable is used to temporarily store each line as it is read, demonstrating effective use of standard input-output streams. By facilitating the management and reading of multiple files, the resource manager illustrates how to apply advanced resource management techniques, ensuring that responsibilities are clearly defined while maintaining efficient resource handling. This centralized approach simplifies interactions with multiple resources, reducing complexity in the broader context of resource management in C++. The displayed pie chart titled Advanced Resource Management Techniques in C++ quantifies the relative emphasis placed on different techniques. Rule of 3, 35%, Smart Pointers 30%, Move Semantics 25%, Resource Manager 5%, and Ownership Semantics 5%. The key pattern is a heavy concentration, 90% combined, on the first three categories: Rule of 3, Smart Pointers, Move Semantics, which indicates that foundational correctness, Rule of 3, modern RAI-based approaches, Smart Pointers, and efficient transfer of resources, Move Semantics, dominate the topic. The two smallest slices, Resource Manager and Ownership Semantics at 5% each, imply that specialized centralized managers and explicit ownership model notation receive much less emphasis in the dataset represented. From these proportions, we can conclude that mastering the core mechanics of copying, RAI, and moving will yield the largest benefit for robust resource handling, while implementing specialized managers or distinct ownership frameworks is more situational. This visual breakdown directly supports prioritizing learning and design effort. Ensure that classes correctly implement copy semantics when owning resources, prefer smart pointers where practical to leverage automatic cleanup, and employ move operations to avoid expensive copies. Consider resource manager patterns and explicit ownership semantics when dealing with multiple resources or complex ownership graphs. Now let's see how we can simplify memory management in our dynamic array class by leveraging smart pointers. We will implement a new class, Smart Dynamic Array, which utilizes STD, unique PTR, to manage a dynamic array of integers automatically. The use of STD, unique PTR, ensures that the dynamically allocated array's memory is automatically cleaned up when the Smart Dynamic Array instance goes out of scope, eliminating the need for a manual destructor. In the constructor of Smart Dynamic Array, we initialize size and create the array member using STD, make unique, which allocates an array of integers of the specified size. This approach not only simplifies memory management, but also enhances performance by avoiding the pitfalls of manual memory handling. What's particularly noteworthy here is that the destructor doesn't need to be defined explicitly. STD, unique PTR, takes care of releasing the memory when the object is destroyed. With this implementation, we significantly reduce the risk of memory leaks and dangling pointers, which can occur with traditional dynamic memory management. This example clearly illustrates the advantages of using smart pointers to align with modern C++ practices. As we wrap up discussing these advanced resource management techniques in C++, it's crucial to recognize the importance of understanding how to manage resources effectively. We've seen how the rule of 3 and the rule of 5 guide us in creating robust classes that handle resources correctly. Additionally, leveraging move semantics improves performance by allowing resources to be transferred rather than copied. Integrating smart pointers into our designs simplifies resource management by using RAI principles, which help us avoid memory leaks and dangling pointers. By adhering to best practices in resource management, not only do we create more efficient applications, but we also enhance the stability and safety of our code. In conclusion, the responsibilities of resource management in C++ require diligence and a clear understanding of ownership. By mastering these techniques, you can ensure your classes handle resources cleanly and efficiently, keeping your applications running smoothly. In our next session, we will explore move semantics further, providing additional strategies to optimize resource management and performance in your C++ programs. Thank you for joining me today. Happy coding. In C++, managing the lifetime of objects is crucial for writing robust and efficient code. Understanding how and when objects are constructed and destructed can save you from memory leaks and undefined behaviors that could lead to difficult-to-debug errors. Today, we will dive deep into object lifetime management, exploring how automatic objects are destructed at the end of their scope in a well-defined order. Now let's take a look at a simple class definition that showcases automatic object management in C++. We define a class called tempObject, which has a constructor and a destructor. The constructor outputs a message indicating when a tempObject is created, while the destructor informs us when the object is destructed. This clear messaging allows us to visualize the life cycle of the object as it enters and exits its scope. Next, we will implement a function named createTemp. Inside this function, we instantiate a tempObject called obj. Since obj is an automatic object, it is allocated on the stack and will be destructed automatically when the function scope is exited. This means that as soon as createTemp completes execution, the destructor for obj is called, producing a message that confirms the object's cleanup. The beauty of this design lies in its simplicity. We do not have to manually manage the memory, letting C++ handle it for us. This seamless process emphasizes the importance of automatic object management and demonstrates how it helps prevent memory leaks and undefined behavior. The figure titled Understanding Object Lifetime Management in C++ is a donut chart divided into 4 labeled slices with clear percentages: automatic objects 40%, dynamic objects 30%, exception safety 20%, and smart pointers 10%. The largest slice, automatic objects at 40%, highlights a strong emphasis on stack-allocated objects and their predictable, scope-bound lifetimes. This supports the lesson's recommendation to prefer automatic storage when possible. The next largest slice, dynamic objects at 30%, indicates that heap allocation remains a significant part of resource management, but is recognized as less preferable than automatic allocation. Together, these two categories account for 70% of the chart, showing that storage duration, stack versus heap, is the dominant concern in lifetime management. Exception safety occupies 20%, underscoring that proper destructor behavior and RAII are critical for reliable cleanup across abnormal control flows, a clear visual cue that exception handling belongs near the top of priorities. Smart pointers at 10% form the smallest slice, but still represent an important tool for safely managing dynamic objects. The chart's proportions suggest that while smart pointers are not the primary focus, they are the recommended mechanism to address the risks associated with dynamic allocation. From these proportions, we can draw practical conclusions that align with the lesson. Prefer automatic objects for most cases, be judicious with dynamic allocation, and pair it with smart pointers, and always design destructors and RAII patterns with exception safety in mind so that resources are released reliably. Now let's see how we can implement exception handling while ensuring proper resource management with automatic objects in C++. In the provided code, we define a function called createTempWithException, where we instantiate a temp object as an automatic object. This means that temp object is created on the stack, and its destructor will automatically be called when the function scope ends, even if an exception is thrown. Here, we deliberately trigger an exception using throw_std, runtime error, something went wrong. This showcases C++ robust exception handling mechanism, which guarantees that the destructor for obj is invoked, allowing for proper cleanup of resources. This behavior ensures that we do not face memory leaks or resource exhaustion, even when extraordinary situations arise unexpectedly. As a result, when the exception is thrown, we can be confident that any resources held by obj are released correctly, demonstrating a fundamental principle of C++ programming: exception safety through automatic resource management. The printed destruct message acts as a verification that the destructor was indeed called, reinforcing the importance of managing resources efficiently. Now let's see how we can implement object destruction and the order in which it occurs. In this example, we define two classes, first and second, each with a constructor and a destructor. The constructors print messages when the objects are created, while the destructors print messages upon destruction. The function demonstrateDestructionOrder creates instances of both classes, starting with an object of first followed by an object of second. When we run this function, we'll notice that the constructors output messages indicating the order of creation. First is created, and then second. This serves to illustrate that objects are constructed sequentially as they are defined in the code. However, when the function scope ends and the destructor for each object is called, the destructors are invoked in reverse order of construction, following the last in, first out principle. Consequently, second is destructed before first. This behavior is crucial, particularly if one object depends on the other during destruction. Understanding this order helps prevent potential errors that can arise from improper dependency management when objects are destroyed. Now let's take a look at how dynamic memory allocation works in C++ by examining a sample class and a function that utilizes it. We start with the dynamic object class, which features a constructor that outputs a message upon creation and a destructor that announces when the object is destructed. This clear demonstration of object lifecycle management showcases how constructors and destructors work within the context of dynamic memory. Next, we have the useDynamicObject function, where an instance of dynamicObject is allocated on the heap using the new keyword. This means the object won't be automatically destructed when it goes out of scope. Instead, it remains in memory until we explicitly call delete. This highlights a key aspect of dynamic allocation. Developers must take responsibility for freeing memory to avoid leaks, which can occur if delete is omitted. In this function, we can also envision expanding the logic surrounding dynobj, performing operations on it as needed. Finally, we must remember to delete dynobj, emphasizing the importance of diligent memory management practices in C++. To wrap things up, let's quickly go over key points on object lifetime management in C++. Automatic objects are destructed at the end of their scope in a defined last in first out order, making memory management straightforward and safe for most common use cases. Exception safety ensures that even when an execution path is interrupted, destructors are still called, mitigating memory leak risks. However, in scenarios requiring extended object lifetimes, dynamic memory management comes into play, where you must be attentive to resource management, particularly in avoiding memory leaks through timely deletions or using smart pointers for automatic cleanup. So today we've discussed object lifetime management in C++, delved into the intricacies of automatic vs dynamic objects, and explored destructors' role in resource management. The more you understand these concepts, the better you can write efficient and effective C++ code. Keep practicing and happy coding. Memory leaks can be a programmer's worst nightmare. They happen when a program allocates memory but forgets to deallocate it, leading to wasted resources and potentially crashing the application. In today's session, we will deeply explore the consequences of memory leaks and the various strategies for managing memory effectively in C++. So far, we learned about the crucial importance of managing object lifetime in C++, especially with automatic objects that are destructed at the end of their scope. We discussed how exception handling ensures that destructors are called even in unexpected situations, maintaining resource integrity. Additionally, we compared automatic and dynamic object management, highlighting the necessity of careful memory management with the latter to avoid leaks. Finally, we emphasized the utility of smart pointers in automating resource cleanup for dynamically allocated objects. Now, we will cover memory leak consequences and effective management strategies. Now let's take a look at a simple example that illustrates a memory leak in C++. In this code, we define a function called memoryLeakExample, where we dynamically allocate an integer on the heap using the new operator and assign it the value of 42. This allocation creates a pointer, lectMemory, which points to that integer. After the allocation, we proceed to print the value stored in the integer using std_count. However, as we continue with the function, you'll notice that we fail to call delete on lectMemory before the function exits. This oversight leads to a memory leak because the allocated memory remains inaccessible and is not released back to the system. Each time this function is called without correctly deallocating the memory, it consumes more and more of the system's resources, which could ultimately lead to performance degradation or even application crashes. This example effectively demonstrates the critical importance of managing dynamic memory in C++ to prevent such leaks and maintain reliable application performance. Now that we understand the problem, let's explore the symptoms and consequences of memory leaks. The most immediate consequence is increased memory usage. You might not notice this immediately for small leaks, but over time they can accumulate, leading to increased memory consumption. Eventually, your application can run out of memory altogether, resulting in an allocation failure where the program cannot allocate more memory even when it needs it. With larger applications or those running on constrained environments like embedded systems or older machines, memory leaks can make the system sluggish. You may start to experience performance issues, spikes in memory usage, or even crashes, definitely not an ideal scenario for any software developer. Imagine a web server that handles incoming requests. If there's a memory leak in the request handling logic, that server could run out of memory and crash, causing downtime. This translates to lost revenue, frustrated users, and loss of reputation. It's critical to avoid such scenarios by implementing effective memory management strategies. Now let's see how we can implement the RAII principle in our code with a simple class named managedResource. This class demonstrates effective memory management by allocating memory for an integer in its constructor. when an object of managed resource is instantiated, the constructor invokes dynamic memory allocation using new, which assigns a value of 100 to the resource and prints a message confirming the allocation. Importantly, the class includes a destructor, which automatically deallocates the memory when the object goes out of scope. This cleanup process is crucial. It prevents memory leaks by ensuring that the allocated memory is freed when the object's lifetime ends. When the function test_RAI is executed, and raise goes out of scope at the function's conclusion, the destructor is called, which performs the necessary cleanup. By allowing the constructor to manage allocation and the destructor to handle deallocation, we can simplify memory management in C++ and significantly reduce the chances of memory leaks, showcasing why RAI is a best practice in resource management. The displayed horizontal bar chart titled Consequences of Memory Leaks and Management Strategies quantifies 4 specific consequences and their relative impacts as percentages. Increased memory usage at 50%, degraded performance at 30%, application crashes at 15%, and inefficient resource allocation at 5%. The bars are arranged top to bottom in descending impact, making the dominant pattern immediately clear. Increased memory usage is the primary and most significant consequence, accounting for half of the measured impact. Degraded performance is the second major effect at nearly 1/3 of the impact, indicating that leaks not only consume RAM but also noticeably slow systems. Application crashes, while less frequent or impactful than the first two, remain a serious concern at 15%, showing that leaks can escalate to fatal failures in some cases. Inefficient resource allocation appears with a small but non-zero impact, 5%, suggesting that while it's a lesser issue compared to raw memory growth and performance hits, it still contributes to overall system inefficiency. The x-axis scale 0-60%, and the explicit percentage labels on each bar provide precise context for prioritization. Mitigation efforts should first target mechanisms that prevent uncontrolled memory growth and performance degradation, then address crash prevention and resource allocation practices as complementary objectives. Now let's see how we can implement smart pointers in C++ using std, unique PTR. In this example, we begin by creating a std, unique PTR named smartPTR, which is responsible for managing an integer object allocated on the heap with the value of 42. The power of std, unique PTR, lies in its ownership semantics. It guarantees that the memory it points to will be automatically freed when the smart PTR goes out of scope. This eliminates the need for manual memory management and the associated risk of memory leaks. Within the function, we display the value of the integer being pointed to by dereferencing smartPTR. This is a straightforward operation, but it demonstrates how you can access dynamically allocated memory safely. Importantly, because we are using a unique pointer, we do not need to call delete explicitly. The memory will be released automatically when smartPTR is destructed at the end of the function. This feature of automatic cleanup significantly enhances resource management and allows programmers to focus on other aspects of their code without worrying about memory leaks. Now let's see how we can implement proper ownership management in C++ with the following example. Here, we define 2 functions, correct ownership and incorrect ownership, illustrating the importance of managing dynamic memory correctly. In correct ownership, we accept a pointer and demonstrate responsible memory management by using the delete statement to deallocate the memory when it's no longer needed. This approach prevents memory leaks by ensuring that the resource is freed appropriately as the function takes ownership of the pointer. On the other hand, the incorrect ownership function shows what happens when we allocate memory using new but forget to release it. We create a pointer that holds a dynamically allocated integer, but without a corresponding delete, the memory it points to remains allocated after the function exits. This oversight leads to a memory leak, which can accumulate if this function is called multiple times, ultimately consuming system resources. Understanding these distinctions is crucial, as it empowers you to manage memory effectively and avoid the pitfalls that lead to leaks, thereby ensuring better application stability and performance. Now let's see how we can use Valgrind to help detect memory leaks in our applications. By running the command valgrind leakcheck equals full, your program, we allow Valgrind to meticulously monitor memory usage throughout the execution of our program. This tool generates a detailed report highlighting any instances where memory was allocated but not freed, which is crucial for pinpointing potential leaks. As the command runs, Valgrind tracks all memory allocations and deallocations, making it easier to identify problematic code sections that may be causing issues. By integrating this tool into our testing process, we can significantly reduce the time spent debugging memory-related problems, as it provides clear indicators of where memory management failures are occurring. Additionally, it enables us to see the context of each memory allocation and deallocation, helping us to understand how our program interacts with dynamic memory. This proactive approach ensures that we can address memory leaks before they escalate and impact application performance or stability. To summarize, memory leaks pose significant consequences for application performance and reliability. Effective management strategies include adopting RAI principles, leveraging smart pointers, understanding pointer ownership, and implementing robust testing practices to catch leaks early on. In the fast-paced world of software development, mastering these strategies can save you countless headaches and ensure your applications run smoothly. Remember, memory management might sound daunting, but with proper practices in place, you can focus on building great features while letting C++ handle the behind-the-scenes memory work. Keep these strategies in mind and happy coding. Managing object lifetimes is a pivotal aspect of C++ programming, intertwining performance and safety seamlessly. This flexibility, while powerful, adds complexity to how we handle memory and object management, making it crucial for developers to understand the intricacies involved in object lifetime management. Now let's take a look at a simple example of stack allocation in C++. In this code, we define a function that declares a local variable named local variable, which is initialized with the value 5. This variable is allocated on the stack, meaning it is handled automatically by the C++ runtime. As soon as the function is called, local variable comes into existence and resides in the stack memory, and when the function completes its execution, local variable goes out of scope and is automatically destructed. The beauty of this approach lies in its simplicity and efficiency. There's no need for manual memory management, effectively minimizing the chance of memory leaks in this context. When the function is exited, the stack will reclaim the memory allocated for local variable, ensuring clean resource management. However, it's crucial to remember its limitations. Variables allocated on the stack cannot be returned from the function because they would be destructed as soon as the function exits. This example highlights the strength of stack allocation for local variables, while also prompting the need to consider other allocation methods when object lifetimes extend beyond function scope. Now let's see how we can implement dynamic memory allocation using heap allocation in C++. In the example provided, a function named dynamic memory allocation is defined, demonstrating how to allocate an integer on the heap. Here we use the new keyword to request memory for an integer and initialize it with the value 10. This integer's address is stored in a pointer, ptr, which gives us access to the allocated memory. Next, we display the value stored at that memory location using the pointer dereference operator. It's important to note that the integer remains in memory until we explicitly deallocate it. That's where the delete keyword comes into play. It's used to free the memory associated with ptr, preventing memory leaks. This example highlights the manual control we gain over object lifetimes with heap allocation. However, we must be cautious and responsible, as failing to properly deallocate memory can lead to memory leaks and resource waste, underscoring the importance of managing memory effectively in C++. Now let's implement an example using std, unique PTR, to demonstrate its capabilities in managing dynamic memory safely. In this code, we first include the necessary headers for memory management and input-output functionality. The function unique pointer example showcases how std, unique PTR, allocates an integer on the heap with a value of 20. As we instantiate std, unique PTR int PTR, we pass a new integer to the constructor which takes ownership of the allocated memory. This means that the unique PTR will handle the memory cleanup automatically. Afterward, we output the value pointed to by PTR, demonstrating that we can access the integer just like a regular pointer. The crucial aspect here lies in the automatic resource management feature of unique PTR. When the unique PTR goes out of scope at the end of the function, its destructor is invoked, which in turn calls delete on the pointer it manages. This prevents memory leaks, simplifying memory handling and ensuring that resources are freed appropriately. By implementing this pattern, developers can confidently manage resources without the risk of forgetting to deallocate memory, thus enhancing the safety and reliability of their C++ applications. Now let's see how we can implement shared ownership using STD, shared PTR. In this example, we start by creating a shared PTR, that manages a dynamically allocated integer with the value 30. This pointer takes ownership of the resource, ensuring its automatic memory management. Next, we introduce another shared PTR2, which is assigned to shared PTR. This assignment allows both pointers to share ownership of the same integer resource. Even though shared PTR2 goes out of scope at the end of the inner block, the resource remains allocated because shared PTR still holds the reference to it. This characteristic of shared PTR effectively prevents memory leaks, as it guarantees that the resource is deallocated only when the last shared PTR referencing it, in this case, shared PTR, goes out of scope. Lastly, we print the value stored in the resource after shared PTR2 has gone out of scope, demonstrating that the resource persists beyond the scope of a single pointer. This example highlights the efficiency and safety of managing object lifetimes with shared PTR, especially in complex scenarios where multiple references to a resource could exist. The figure titled Memory Management Techniques in C++ presents a bar chart comparing 4 techniques by an efficiency percent scale from 0 to 100. The x-axis lists the techniques: stack allocation, heap allocation, smart pointers, and memory leaks. The visible bar heights and numeric labels above each bar indicate the measured values: stack allocation at 50%, heap allocation at 30%, smart pointers at 80%, and memory leaks at 20%. From these values, we can directly observe that smart pointers have the highest reported efficiency, 80%, roughly 1.5 times that of stack allocation, 50%, and more than double heap allocation, 30%. Memory leaks register the lowest efficiency at 20%, clearly separated from the other techniques. The chart's scale to 100% situates each technique as a proportion of maximum efficiency, making it evident that smart pointers dominate in this comparison. Stack allocation is moderate, heap allocation is relatively low, and memory leaks are detrimental to efficiency. Next, we will write the following code to understand how STD, weak PTR, works in conjunction with STD, shared PTR. In this example, we create a shared PTR that manages an integer initialized to 40. Immediately, we establish a weak PTR, which references the same integer without increasing its reference count. This is crucial as it means that the weak PTR does not prevent the managed object from being destroyed when the last owning shared PTR goes out of scope. As we examine the use count before entering a new scope, we can observe it being 1, indicating that only the shared PTR is currently managing the resource. Upon entering the scope, we utilize the lock function of the weak PTR to attempt to acquire a shared PTR. This is an important feature as it checks whether the resource is still valid before attempting to reference it. If the resource is still available, we display its value. After the inner scope concludes, shared PTR2 goes out of scope, and the use count remains 1, reaffirming that the resource is still managed by the original shared PTR. This example highlights how weak PTR can effectively prevent memory leaks resulting from circular references, especially in complex data structures. Now let's take a look at how destructors play a fundamental role in resource management within a C++ class. The sample class here demonstrates the use of both a constructor and a destructor. The constructor is defined to print a message when an object of the class is created, indicating that the object is being initialized. This feedback is crucial for understanding the flow of object creation in your programs. When we instantiate an object of the sample class inside the destructor example function, the constructor executes and constructor called is printed to the console. This is followed by the exit of the function where the local variable obj goes out of scope. At this point, the destructor is automatically invoked, executing the cleanup code in the destructor that prints destructor called. This automatic invocation of the destructor is a key feature of C++, ensuring that resources are freed when they are no longer needed. Understanding this lifecycle behavior is essential in managing resources effectively, as it reinforces the importance of considering object lifetimes in your programming practice. Now let's implement the following class to demonstrate the rule of 3 in C++. The rule of 3 class encapsulates manual memory management through the use of a raw pointer, data, which dynamically allocates memory for an integer. The constructor initializes this pointer by allocating memory for an integer based on the provided value, ensuring that our object has its own resource right from the start. Next, we define a custom destructor, which is crucial for cleaning up the allocated memory when the object goes out of scope. This prevents memory leaks, ensuring that our program runs efficiently without holding onto resources unnecessarily. Additionally, we implement a copy constructor, which takes in another rule of 3 object and allocates its own memory for data, copying the value safely from the other object. This guarantees that both objects can operate independently without interfering with each other's resources. Finally, the copy assignment operator ensures that if an object is assigned to another, it cleans up any existing memory before taking ownership of the new resource. This careful management of memory through explicit constructors and destructors showcases how to adhere to the rule of 3, vital for developers who need to prevent memory leaks and maintain robust object management in their applications. Now let's implement the following example that illustrates the rule of 5 in C++. The rule of 5 class includes a pointer data that dynamically allocates memory to store an integer. The constructor initializes this pointer with a new integer value, ensuring that resources are allocated when a rule of 5 object is created. The destructor is essential, as it ensures that memory is properly released to prevent leaks. Next, we define the copy constructor, which creates a deep copy of the integer by allocating new memory and duplicating the value from another instance. This approach helps maintain separate ownership of resources. Similarly, the copy assignment operator checks for self-assignment before releasing any existing memory and copying the data from another instance. Now let's see how we can enhance efficiency by incorporating move semantics. The move constructor transfers ownership of the data pointer from a temporary object, nullifying the original pointer to avoid double deletion. Finally, the move assignment operator similarly transfers resources while ensuring the existing resource is cleaned up. This robust management of object lifetimes reflects best practices in C++, allowing for safe and efficient resource handling. In our exploration of object lifetime management techniques, we have covered stack and heap allocation, the importance of ownership and smart pointers, including unique PTR, shared PTR, and weak PTR. We've also discussed destructors, the rule of 3, and the rule of 5. Knowing how to manipulate the life cycle of objects in C++ allows you to write robust and efficient applications. By implementing these strategies, you ensure that your applications are not only efficient, but also safe from memory-related issues that can cause performance bottlenecks or crashes. In conclusion, understanding and effectively managing object lifetimes is essential for any C++ programmer who aims to build high-quality software. Thank you for tuning in and keep coding. Managing resources in C++ is a critical skill for any developer looking to build efficient and robust applications. Today, we will delve deeper into advanced resource management strategies that can help you master this essential aspect of programming. So far, we learned about managing object lifetimes in C++, focusing on both stack and heap allocations. We emphasized the importance of ownership with smart pointers like unique PTR, shared PTR, and weak PTR, along with discussing the role of destructors. Additionally, we covered the rule of 3 and the rule of 5 for effective resource management. These principles provide a framework for writing efficient and safe C++ applications. Now we will talk about how the default-generated special functions often do not meet our needs when we explicitly manage resources. Now let's take a look at a simple class designed to manage a dynamic array. This dynamic array class consists of two main attributes, a pointer to an integer array and its size. In the constructor, we allocate memory for the array on the heap using the new operator, providing flexibility in how much space to allocate based on user input. Next, we see the destructor implementation. It's crucial to release the allocated memory properly to prevent memory leaks. The destructor uses delete to ensure the entire array gets freed when the object goes out of scope. However, if we create a second instance of this class using the default copy constructor, we may encounter significant issues. The default behavior simply copies the pointer to the data array, resulting in two objects pointing to the same memory address. When one instance is destroyed, the other ends up with a dangling pointer, which can lead to undefined behavior. To address these issues, we will eventually need to implement custom copy and assignment functionalities, ensuring that resources are managed correctly. This will illustrate the importance of handling deep copies for classes managing their own resources, highlighting key strategies in resource management. Now let's implement the following advanced resource management techniques specifically tailored for our dynamic array class. We begin by defining a copy constructor that enables deep copying of dynamic arrays. This means when we create a new dynamic array from an existing instance, it allocates its own memory space for data, ensuring that changes to one instance do not affect the other. Next, we introduce the copy assignment operator, which includes a self-assignment check. This is crucial because if we end up copying an instance to itself, we want to avoid unnecessary deletions and allocations. If the instances are different, it first deallocates any existing memory, then allocates a new array and copies the elements from the source array. We also implement a destructor to free the dynamically allocated memory when an object goes out of scope. This is essential for preventing memory leaks. By incorporating these features, we adhere to the rule of three, gaining the ability to manage resources safely and efficiently, ensuring each dynamic array maintains its own copy of the data and handles its life cycle properly. Through this, we are equipped to deal with dynamic memory in a reliable manner. Now, let's implement the move semantics in our dynamic array class to enhance resource management. The move constructor is designed to efficiently transfer ownership of resources from one object to another without duplicating them. It takes a parameter of a temporary dynamic array object and moves its internal pointer and size to the new instance. Crucially, it nullifies the data pointer of the source object to avoid double deletion, ensuring that the original object remains in a valid state. Next, we focus on the move assignment operator, which is similar in spirit. It checks for self-assignment to avoid unnecessary operations. If the instance is indeed being assigned a new resource, it first cleans up any existing resource to prevent memory leaks. It then transfers the ownership of the data pointer and size from the temporary object, again leaving the source in a nullified state. These additions not only improve the performance of temporary object management, but also ensure that resource handling is done cleanly, minimizing the risk of memory-related issues. By incorporating these features, our dynamic array class efficiently manages resources, aligning with the rule of five principles we previously discussed. The figure displays a horizontal bar chart titled Efficiency of Resource Management Strategies in C++ with 4 categories and their efficiency ratings. Rule of 3 at 70%, Rule of 5 at 85%, Smart Pointers at 90%, and Manual Management at 40%. Key patterns are immediately visible. Smart Pointers have the highest reported efficiency, 90%, followed closely by Rule of 5, 85%, indicating that adopting move semantics yields a substantial improvement over older copy-based practices. The Rule of 3 at 70% sits notably lower than Rule of 5, showing a roughly 15 percentage point gap that quantifies the performance and safety benefits of adding move operations. Manual management is the lowest at 40%, creating a pronounced contrast, a 50-point gap against smart pointers, and highlighting the relative inefficiency and higher risk associated with manual resource handling. From these values and their relative bar lengths along the 0-100% axis, the clear conclusion is that smart pointers and modern move-aware designs provide the best efficiency profile among the strategies shown, while manual management lags far behind. Now let's take a look at a class that manages file handles, ensuring that resources are handled properly to avoid leaks. This class, File Wrapper, encapsulates a file stream using the fstream library to safely open and close files. In the constructor, we open a file specified by the user, combining input and output modes. It's essential to manage the file carefully, so we check whether the file is open before attempting to close it in the destructor. This prevents potential issues like trying to close a file that is not actually open, which could cause runtime errors. A key consideration when managing resources like file handles is the need for custom copy and move semantics. If we were to add copying support to File Wrapper without careful implementation, 2 instances could accidentally try to manage the same file handle simultaneously, leading to undefined behavior. Therefore, implementing custom copy and move constructors allows for safe and clear ownership management. This ensures that when one instance of File Wrapper is destructed, it does not interfere with another, maintaining the integrity of resource management within your applications. Next, we will implement a simple socket class to manage network connections, focusing on ensuring unique ownership of resources. In this class, we start by defining a private integer to store the socket file descriptor. The constructor is responsible for initializing the socket by creating a connection using a given address and port. Now let's see how we manage ownership in this class. We prevent copying by explicitly deleting the copy constructor and copy assignment operator. This design choice is crucial because it ensures that only one instance of the socket class can own a particular socket resource, thus preventing accidental duplication and potential resource conflicts. Next, we implement move semantics, which allows for efficient transfer of ownership without duplicating resources. The move constructor takes in an R-value reference of another socket instance, transferring the socket file descriptor and invalidating the moved from instance by setting its file descriptor to an invalid state. Similarly, the move assignment operator checks for self-assignment and safely cleans up any existing resources before transferring ownership. Finally, the destructor ensures proper cleanup by closing the socket if it is still valid, safeguarding against resource leaks. Through these features, the socket class exemplifies effective resource management and clear ownership semantics in C++. As we finalize our discussion on advanced resource management strategies, it's important to highlight some best practices. Always ensure to document ownership semantics clearly. It will help others and your future self understand how to use your classes without inadvertently causing resource leaks. Moreover, use smart pointers when suitable. They can reduce the boilerplate code associated with manual resource management while still allowing for efficient and clear ownership semantics. In conclusion, mastering advanced resource management strategies in C++ is paramount. It allows you to design robust, efficient, and maintainable code. By combining the principles of the rule of 3 and the rule of 5 with a deep understanding of ownership semantics, you ensure that your applications run smoothly, free from memory-related issues. By taking control of the life cycle of your objects, you grant yourself the power to build better software solutions. Thank you for tuning in, keep coding, and remember, effective resource management is the backbone of excellent C++ programming. Understanding object lifetimes in C++ is crucial for effective memory management and resource control. Automatic objects are typically destroyed at the end of their scope, which is defined in a precise order that maintains program stability and efficiency. Today, we'll dive deeper into how this works and explore examples to illuminate the concept. So far, we learned about the importance of managing resources in C++, focusing on control over object lifetimes through the rule of 3 and the rule of 5. We discussed implementing custom copy constructors and assignment operators to prevent issues like dangling pointers and memory leaks, particularly when dealing with dynamic memory. Additionally, we introduced move semantics to enhance performance by efficiently transferring resource ownership. Finally, we emphasized the significance of clear documentation and understanding of ownership semantics in resource management practices. Now we will cover the specific details of object lifetimes, how automatic and dynamic objects behave, and the significance of proper scope and order of destruction in C++. Now let's take a look at a simple example that illustrates the life cycle of automatic objects in C++. We will define two classes, A and B, where class B contains an instance of class A. The constructors and destructors of both classes are explicitly defined to showcase how object creation and destruction are managed. In the main function, we create an instance of class B, named B. When B is instantiated, the constructor of B is called first, which in turn triggers the constructor of A due to class B, holding an instance of A. This sequence of events demonstrates how automatic objects are created in a defined order. As the program executes and B goes out of scope when main ends, the destructors are called in the reverse order. First, the destructor of B is invoked, followed by the destructor of A. This ordered destruction is critical for proper resource management, ensuring that all resources are released appropriately and preventing memory leaks or dangling references. Through this example, we can clearly see how automatic objects operate within their defined scopes, reinforcing the importance of understanding object lifetimes in C++. The bar chart titled Key Concepts of Object Lifetimes in C++ displays 5 categories on the x-axis: automatic objects, dynamic objects, scope, RAI, and smart pointers, with the y-axis labeled as importance % and values annotated on top of each bar. The numeric heights are automatic objects equals 40, dynamic objects equals 35, scope equals 15, RAII equals 25, and smart pointers equals 30. From these values, we can draw several points. Automatic objects have the largest single percentage, 40%, indicating the greatest emphasis on stack-allocated lifetimes and the safety they provide through deterministic destruction. Dynamic objects are close behind at 35%, reflecting the substantial importance of explicit heap management and the risks involved if not handled carefully. Smart pointers at 30% show strong support for modern ownership abstractions that reduce manual delete calls and help manage dynamic lifetime. RAI at 25% underscores the pattern's role in bundling resource acquisition with object lifetime, while scope at 15%, the lowest value, suggests that although lexical scope underpins lifetime rules, the more actionable concerns in practice are dynamic allocation and ownership patterns. The distribution highlights a balanced lesson takeaway. Favor automatic objects when possible, apply smart pointers and RAI to manage dynamic resources, and recognize scope as the underlying mechanism that enforces deterministic destruction. The annotated values and the relative spacing between bars make it clear which concepts the lesson emphasizes and how they relate in priority to each other. Now let's see how we can implement a dynamic object in C++ with careful memory management. The code defines a simple class called dynamicExample, which contains a constructor and a destructor. The constructor outputs a message indicating that a dynamicExample object has been created, while the destructor signals that the object is being destroyed. This illustrates the life cycle of dynamic objects. In the main function, we dynamically allocate an instance of dynamicExample using the new keyword, storing the pointer in obj. Since this object resides on the heap, it does not automatically clean up when it goes out of scope, making it essential to manage its lifetime explicitly. To avoid memory leaks, a scenario where allocated memory is not released, we must remember to call delete on obj before the program ends. This action invokes the destructor, ensuring that any resources associated with the dynamicExample instance are properly released. By implementing this code, students can appreciate the importance of explicit memory management when working with dynamic objects in C++, reinforcing the lesson on resource control and object lifetimes. Now let's take a look at a practical example that illustrates the concept of automatic object lifetimes in C++. In this snippet, we define a function called createObject that instantiates two automatic objects, and bb. Both objects are created on the stack, meaning they will be destroyed automatically when the function exits. This characteristic of automatic objects ensures that their destructors are called in reverse order of their construction, thus maintaining a clear and predictable resource management pattern. Upon calling createObject, the constructor for class A is executed, followed by the constructor for class B. This is a vital aspect of C++. As the function execution ends, the destructors will be invoked in the opposite order, ensuring B is destroyed before A. This structure highlights the significance of scoping rules in C++, where each level of nesting creates its own specific context for object lifetime management. This not only prevents memory leaks, but also reinforces the concept of deterministic destruction. Next, we see how these automatic objects allow for well-defined lifetimes, enhancing stability and safety within our programs. Now let's take a look at how we can effectively manage dynamic object lifetimes in C++ using smart pointers. In the provided code, we introduce the std, unique PTR, a smart pointer that automatically takes care of memory management for dynamic objects. Here, the smart pointer example class features a constructor and a destructor that display messages when an object is created and destroyed, respectively. In the main function, we instantiate a std, unique PTR called sb, which points to a new instance of smart pointer example. This allocation on the heap would traditionally require manual memory management, likely needing a corresponding delete call to prevent memory leaks. However, with std, unique PTR, there's no need for that. When sb goes out of scope, it automatically calls the destructor of smart pointer example, ensuring that the memory is freed properly. This automatic resource management not only enhances your code's safety, but also simplifies memory handling, minimizing the risk of leaks. By leveraging smart pointers, you gain precise control over object lifetimes while still taking advantage of dynamic memory allocation in modern C++. Now let's take a look at the resource acquisition is initialization RAII approach in action. In the code, we define a class called resource, which features a constructor and a destructor. The constructor outputs a message indicating that the resource has been acquired, while the destructor provides feedback that the resource is being released. Next, we implement a function with resource, where an instance of resource is created. Here, the moment we declare resource raise, the constructor is invoked and the resource is acquired. This illustrates an important aspect of RAII. The resource's lifecycle is tied directly to the object's scope. As the function executes and eventually exits, the destructor of resource is automatically called, indicating the resource is released without any additional code required for cleanup. Finally, in the main function, we simply call function with resource. This demonstrates the safety and clarity provided by RAII, as resource management is handled automatically and predictably, reinforcing best practices in C++ for resource control. We have covered how object lifetimes are crucial in ensuring stability and performance in C++. We've seen the differences between automatic and dynamic objects, how scopes affect lifetimes, and the essential roles of smart pointers and RAII in modern C++. By keeping object lifetimes in mind, you're better equipped to manage resources effectively, reducing the risks of memory leaks and undefined behavior. As you continue to program in C++, always bear in mind these principles of resource management. They're key to writing robust, efficient code. In today's lesson, we are going to explore the important topic of managing resource ownership and copy semantics in C++. This is essential for ensuring that our programs run smoothly without memory leaks or resource misuse. So far, we learned about the distinction between automatic and dynamic objects in C++, emphasizing the importance of managing object lifetimes for effective resource control. We explored how automatic objects are destroyed when going out of scope in a defined order, while dynamic objects require explicit deletion to avoid memory leaks. The use of smart pointers and the RAII principle were introduced as modern practices to automate memory management and ensure proper resource release. Overall, understanding these concepts is crucial for writing stable and efficient C++ code. Now we will talk about the rule of three and how to properly implement destructors, copy constructors, and copy assignment operations. The displayed figure is a pie chart titled Key Concepts in Managing Resource Ownership and Copy Semantics in C++, and it partitions emphasis across 5 categories: automatic objects, dynamic objects, resource acquisition is initialization, RAII, smart pointers, and rule of three. The wedges and their relative sizes correspond to values 45, 40, 30, 35, 50, which translate to percentages of the whole. Rule of three is the largest wedge at 25%, automatic objects is next at 22.5%, dynamic objects at 20%, smart pointers at 17.5%, and RAII at 15%. From this visualization, we can draw several conclusions relevant to the lesson. The rule of three occupies the most prominent share, emphasizing its central role in copy semantics and manual resource management. Automatic and dynamic objects together form a majority focus, reinforcing the importance of understanding both stack-based and heap-based lifetimes. And RAII and smart pointers, while clearly important, occupy smaller but substantial wedges, indicating they are key complementary techniques alongside the foundational rule of three. The chart labels each category and annotates the precise percentage for each wedge, making it clear which concepts receive the most emphasis and how modern practices, smart pointers, RAII interact with traditional responsibilities, managing automatic dynamic objects and implementing the rule of three. Now let's take a look at the implementation of our resource class, which effectively demonstrates the rule of three in action. The class begins with a constructor that initializes a dynamic array of integers. When an instance of resource is created, memory is allocated for the specified size, and a message is printed to confirm the acquisition of resources. Next, we must ensure that the resources are properly released when an object goes out of scope, which is achieved in the destructor. This destructor deallocates the memory, preventing memory leaks, and prints a message indicating that the resource has been released. This highlights the importance of resource management in C++. Now, to further reinforce safe resource handling, we need to implement the copy constructor. This constructor ensures that when an object is copied, a new, independent copy of the data is created rather than simply sharing the same memory. This prevents issues like double deletion and dangling pointers. Finally, we implement the copy assignment operator, which enables safe assignment of one object to another. It first checks for self-assignment and properly releases any existing resources before allocating new memory and copying the data. This completes our class, allowing it to manage resources effectively while adhering to the principles of the rule of three. Next, we will implement the copy constructor for our resource class, an essential part of ensuring that our dynamic memory is managed properly. In this constructor, we take a reference to another resource object as a parameter. The first step is to initialize our class members. We set the size to the size of the other object and allocate a new block of memory for data, ensuring that each resource instance maintains its own separate array. We then use std copy to copy the contents from the other object's array into our newly allocated memory. This meticulous copying guarantees that both objects have their own data, thereby preventing issues associated with shared memory ownership, such as dangling pointers. Finally, we include a console output statement confirming that the resource has been copied, which aids in tracking our object manipulations during runtime. Proper implementation of this copy constructor is a critical step in following the rule of three, reinforcing the integrity and safety of our resource management in C++. Now let's see how we can implement the copy assignment operator for our resource class. This operator is crucial when we want to assign one existing object to another, and we must ensure it adheres to the rule of three. In this implementation, we start by checking for self-assignment using the condition, if this equals an other. This safeguard prevents us from mistakenly deallocating memory that we're trying to copy if both objects refer to the same instance. Once we've confirmed this isn't the case, we proceed to release the existing memory with delete data, ensuring that any previously allocated resources are properly freed to avoid memory leaks. After that, we can safely update the size of our resource to match that of the other object. We then allocate new memory for the data array according to the size of other and utilize std copy to duplicate the contents from other data to our new memory. This thorough process ensures that each resource instance maintains its own unique memory, preventing issues of shared ownership and maintaining the integrity of our application. Finally, the method returns a reference to the current instance, allowing for chained assignments and consistent behavior. Now that we've implemented the core elements of the resource class, let's explore how all these pieces come together to manage dynamic memory effectively. First, observe the constructor, which initializes the class by allocating memory for an array of integers based on the input size. This step emphasizes the need for resource acquisition right at the object creation, ensuring that each instance manages its own unique memory. Next, we have the destructor, which plays a critical role in preventing memory leaks. It ensures that when an object of the resource class goes out of scope, its allocated memory is correctly released, thus maintaining the integrity of memory management. Now let's implement the copy constructor. This function deep copies the data from one object to another, allocating new memory to prevent multiple objects from pointing to the same location. This step is vital in maintaining ownership semantics so that each instance has its independent data. Finally, we have the copy assignment operator, which safeguards against self-assignment while facilitating the assignment of one object's data to another. Here, we ensure that any existing resource is released before allocating new memory and copying the contents, thereby preventing memory leaks and dangling pointers. Together, these components exemplify the rule of three, creating a robust and safe way to manage dynamic resources. Now let's see how we can implement the main function that tests the functionality of our resource class, showcasing the principles we discussed about the rule of three. In this snippet, we first create an instance of the resource class named raise1, allocating memory for an array of 5 integers. This triggers the constructor, which outputs a message indicating that the resource has been successfully acquired. Next, we take a look at the copy constructor in action with the line that initializes raise2 as a copy of raise1. This step demonstrates the careful management of resources, where raise2 receives its own allocation and copies the data from raise1, ensuring that both objects can operate independently without interfering with each other's memory. Then we create a third instance, raise3, allocating 10 integers. After that, we assign raise1 to raise3 using the copy assignment operator. This showcases the significance of our operator implementation, where existing resources are safely released before new allocations are made, again adhering to the rule of three to avoid issues like double deletion or memory leaks. Overall, this demonstration illustrates the core concepts of resource management in C++ through effective use of constructors and operators. In conclusion, mastering resource ownership and the rule of three is critical in C++ programming. These principles help us avoid common pitfalls such as memory leaks and dangling pointers. By implementing user-defined destructors, copy constructors, and copy assignment operators, we ensure that our classes handle dynamic memory safely and efficiently. Always remember, in C++, memory management is often your direct responsibility, and understanding these rules is essential for writing robust applications. So next time you find yourself dealing with dynamic resources in your C++ code, think of the rule of three as your guiding principle that safeguards against memory errors and keeps your code clean and effective. Happy coding! Automatic object lifetime management in C++ is a fundamental concept that can make or break your resource handling strategies. In C++, automatic objects, which are typically created on the stack, are destructed automatically at the end of their scope. Understanding how the lifetime of these objects works is essential for writing efficient, stable, and predictable C++ code. So far, we learned about managing resource ownership and copy semantics in C++. We emphasized the importance of the rule of three, which dictates that if a class requires a user-defined destructor, copy constructor, or copy assignment operator, it needs all three to properly manage dynamically allocated resources. We implemented a resource class that demonstrates these principles, ensuring that memory is correctly handled to prevent memory leaks and corruption. Understanding these concepts is vital for writing stable and efficient C++ code. Now we will cover object lifetime management, how destruction works, and why it is essential for system stability. The included bar chart titled Understanding Object Lifetime Management in C++ displays 5 key concepts on the x-axis: automatic objects, dynamic allocation, RAII, smart pointers, and exception safety, with their corresponding importance level on the y-axis. Each bar is annotated with its numeric importance value: automatic objects 40, dynamic allocation 30, RAII 20, smart pointers 25, and exception safety 15. From the heights and values, automatic objects are shown as the most emphasized topic, followed by dynamic allocation. Smart pointers sit in the mid-range, slightly above RAII, while exception safety is represented with the lowest numeric value. The visualization makes 2 clear patterns evident. 1. Stack-based automatic objects receive the highest priority in lifetime management considerations. And 2. While dynamic allocation and smart pointer techniques are important, explicit RAII practices and exception safety receive lower relative emphasis in this depiction. These relative magnitudes suggest focusing study and design attention first on automatic object semantics and careful handling of dynamically allocated resources, then on adopting smart pointers and RAII patterns, with deliberate handling of exception safety concerns as a necessary but comparatively smaller portion of the overall strategy. The chart also includes direct numeric labels atop each bar and a grid on the y-axis, which makes it straightforward to compare exact importance levels across the 5 concepts. Next, we will write an example to illustrate how objects in C++ are automatically managed within their scope. In our example, we define a class called SimpleObject, which has a constructor and a destructor. The constructor outputs a message when an object is created, while the destructor outputs a message when the object is destroyed, demonstrating automatic memory management. Now let's implement a function, createObject, that instantiates SimpleObject. Here, the local variable obj is created within the function's scope. As the function executes, it prints an indication that the object has been created. Upon reaching the end of the function, the scope is exited, and obj is automatically destructed, triggering the destructor's message. This behavior shows how C++ manages object lifetimes through automatic destruction, relieving developers from the burden of manual memory management. Finally, in the main function we call createObject, and after returning from it, we see another message confirming that control has returned. This clear flow showcases the benefits of automatic scope-based management in C++, helping to minimize memory leaks and ensuring efficient resource handling. Now let's see how we can implement object destruction order in C++. In this example, we define two simple classes, first and second, each with a constructor and a destructor that print messages when they're created and destroyed. Inside the scope management function, we create instances of both classes. First is instantiated first, followed by second. Understanding that constructors are called in the order of object creation, it's crucial to recognize how destructors behave. When scope management exits, the destructors are invoked in reverse order. In this case, second is destructed before first. This ensures that if there were dependencies between the objects, second would be safely dismantled before first, preventing potential issues like dangling references. By managing object lifetimes in this way, developers significantly reduce the risks of memory corruption issues. This snippet serves as a vital illustration of C++'s automatic destruction feature, emphasizing the importance of constructor-destructor ordering and proper resource management, which are essential for writing clear, maintainable code. Now let's take a look at how dynamic object management works in C++. In this example, we define a class called dynamicObject, which includes a constructor that outputs a message when an instance is created, and a destructor that confirms the object's destruction when it is no longer needed. The function dynamicManagement demonstrates how to create an instance of dynamicObject dynamically using the new keyword. This means that the object will persist in memory until we explicitly call delete. After creating the object with new, it's important to remember that this object won't be destroyed automatically when it goes out of scope, unlike automatic objects. Therefore, we include a delete statement to free the memory allocated for the object when we are done using it. Failing to do so would result in a memory leak, where the memory remains allocated even after it is no longer in use. This reinforces the importance of managing dynamic memory explicitly to ensure program stability and efficiency. By practicing careful memory management, we can prevent issues associated with dynamic allocation and maintain a clean and effective code base. Now let's see how we can implement exception safety in C++ with our ExceptionSafe class. This class contains a constructor and a destructor that print messages upon creation and destruction, demonstrating the object's lifecycle. Inside the class, we define a method called riskyOperation, which simulates an operation that may throw an exception by using throwSTD, runtime error. Next, we create a function named handleExceptions, which instantiates an exception-safe object named obj. The key aspect here is that if riskyOperation throws an exception, the flow of control will abruptly jump to the corresponding catch block, potentially skipping the call to obj's destructor. This situation can lead to resource leaks, as any resources that obj manages will not be released properly. To handle this, the idea of RAII, resource acquisition is initialization, comes into play. By tying resource management to the object's lifetime and ensuring destructors are called when the object goes out of scope, C++ provides a solid strategy for managing resources resiliently even in the face of exceptions. This mechanism ensures that those resources are always released appropriately, promoting safer memory management practices. Now let's take a look at smart pointers in C++, specifically focusing on STD, unique PTR. This feature streamlines memory management by automatically taking ownership of dynamically allocated objects. In our example, we define a class called SmartPointerExample, which includes a constructor that outputs a message upon creation and a destructor that signals when the object is destroyed. Next, we'll implement the SmartPointerDemo function. Within this function, we declare a STD, unique PTR named PTR, that is initialized with a new instance of SmartPointerExample. The key benefit here is that as soon as the function exits and PTR goes out of scope, the destructor for the managed instance is automatically invoked. This seamless handling of memory signifies the elimination of manual deletion and the potential risks of memory leaks and dangling pointers. By leveraging STD, unique PTR, developers can write cleaner and more maintainable code, allowing them to focus on application logic rather than resource management intricacies. This illustrates how modern C++ features enhance safety and simplicity in object lifecycle management. In conclusion, understanding object lifetime management in C++ is fundamental for writing robust programs. We covered how the automatic destruction of objects at the end of their scope works, the order of destruction, the management of dynamic objects, and the importance of considering exceptions in your code. We also discussed how smart pointers can help manage ownership and lifecycle more effectively. By mastering these concepts, you'll significantly enhance your ability to manage resources efficiently in C++, reducing the risk of memory leaks and ensuring your applications run smoothly. Always remember, when objects go out of scope, their destructors will be called, leaving you free to focus on the logic of your application rather than manual memory management. Happy coding! Managing memory leaks and resource allocation in C++ is crucial for writing efficient and reliable programs. A memory leak occurs when an application allocates memory but fails to release it, causing the system to run out of memory over time. Today we'll explore what happens when we work with pointers, especially focusing on our friend P1. You might be wondering what happens to P1's pointy when it's manually constructed and not destructed. Grab your favorite coding environment and let's dive right in. Next, we will write the following code to demonstrate a memory leak scenario in C++. In this example, we define a function called memoryleakDemo, where we dynamically allocate memory for an integer and assign it the value of 42 using the new operator. The pointer P1 holds the address of this newly allocated memory, allowing us to print the value it points to. However, a crucial mistake occurs here. We do not include a delete statement to free the memory before the function exits. As a result, once memoryleakDemo concludes, the pointer P1 goes out of scope, leaving the allocated memory still reserved, which leads to a memory leak. This situation illustrates the importance of pairwise management of memory allocation and deallocation in C++. As we will see in subsequent examples, neglecting these responsibilities can lead to significant performance issues over time. Understanding this principle is foundational for managing resources effectively in C++ applications. Now let's see how we can implement a solution to the memory leak issue we discussed earlier. In this example, we'll focus on proper memory management by ensuring that dynamically allocated memory is released before the function exits. We begin by allocating memory for an integer using the new operator, which allows us to store a value of 42 in this memory. The pointer P1 points to this allocated memory, and we utilize it to print the value stored. However, an essential step follows. Right before the function concludes, we include a delete P1 statement. This operation frees the memory allocated to P1, effectively returning it to the system and preventing any memory leaks. This illustrates a fundamental principle in C++ memory management. For every allocation made with new, there must be a corresponding delete. By adhering to this guideline, we can significantly reduce the chances of memory leaks and ensure that our programs run efficiently and reliably. This approach is vital, especially in larger applications, where unmanaged memory can lead to performance degradation over time. Next, we will write the following example to demonstrate what happens when an exception occurs after dynamically allocating memory. In this snippet, we see a function called AbstractionDemo, where an integer pointer, P1, is created and initialized to point to a new integer with the value 42. The program then prints this value, showcasing the pointer's utility. However, to illustrate the problem of memory management under exceptions, we introduce a throw statement simulating an unexpected error. This crucial point highlights that if an exception is thrown after memory allocation and before the delete statement, the program jumps out of the normal control flow, and P1 does not get deleted. This ultimately results in a memory leak since the memory allocated for the integer remains reserved, leading to inefficient memory use over time. The follow-up comes in the main function, where we call AbstractionDemo within a try-catch block. While we catch the exception and display an error message, the memory leak from P1 remains a key concern, emphasizing the necessity of effective memory management techniques and the RAII principle to handle such scenarios gracefully. Now let's implement the following example to illustrate the use of smart pointers with STD, unique PTR. In this demonstration, we first include the necessary headers for input-output operations and smart pointers. The smart pointer demo function then creates a STD, unique PTR int, called P1, which allocates memory for an integer initialized to the value 42. This unique pointer takes ownership of the dynamically allocated memory, meaning that we no longer need to explicitly delete it later. Next, we print the value pointed to by P1, confirming that the allocation was successful. The beauty of using STD, unique PTR is that once the smart pointer demo function concludes, P1 goes out of scope and its destructor automatically deallocates the memory it manages. There's no need for an explicit delete statement, reducing the risk of memory leaks and simplifying memory management significantly. This approach embodies the principles of resource acquisition is initialization, RAII, letting smart pointers handle cleanup, ensuring efficient and reliable applications. The accompanying donut chart titled Key Concepts in Managing Memory and Resource Allocation shows the relative emphasis among 5 topics: memory leaks, largest wedge, RAII, smart pointers, dynamic allocation, and exception safety. The chart displays the following proportions: memory leaks. Percent RAII tilde 24, 0%, smart pointers tilde 20, 0%, dynamic allocation tilde 16, 0%, and exception safety tilde 12, 0%. From these values, we can conclude that memory leaks are presented as the single most prominent concern, with RAII and smart pointers together representing a substantial portion of focus, about 44%, indicating that automatic and ownership-based techniques are central to mitigating leaks. Dynamic allocation and exception safety are smaller but still meaningful slices, underscoring that proper allocation patterns and handling errors are necessary complements to RAII and smart pointer strategies. The chart thus reinforces the lesson's narrative. Preventing leaks is the primary goal, and RAII plus smart pointers are key tools in the overall resource allocation toolkit. Now let's see how we can implement STD, shared PTR, to manage shared ownership of a resource in C++. In our example, we begin by creating a shared pointer called P1, which is initialized with a dynamically allocated integer set to 42. This sets the foundation for shared ownership among pointers. We then introduce another shared pointer, P2, which is assigned the ownership of the same resource that P1 manages. This is where the beauty of STD, shared PTR, shines. Even though P2 is instantiated within a separate scope, it shares ownership with P1. When P2 exits its scope, its destructor is called, but the underlying resource remains intact as P1 still holds on to it. Finally, when P1 itself goes out of scope, the destructor is triggered, and the memory allocated for the integer is released automatically. This automatic memory management not only reduces the risk of memory leaks, but also simplifies resource sharing in applications. By using STD, shared PTR, developers can confidently manage resources in scenarios where multiple entities need to work with the same piece of data without worrying about explicit memory deallocation. To summarize, managing memory effectively in C++ is paramount to developing reliable and efficient applications. We learned that without proper memory management, we can end up with memory leaks that can overwhelm the system. We explored the concept of allocating memory with new, ensuring to pair it with delete to prevent leaks. We also addressed the challenges posed by exceptions and how RAII can help mitigate such issues. Moreover, we saw how smart pointers like STD, unique PTR, and STD, shared PTR, simplify resource management by automatically handling the deallocation of memory. This empowers developers to focus more on the actual logic of their applications rather than micromanaging memory. Remember, whether using basic pointers or the modern smart pointers, always think carefully about memory allocation and deallocation. This will help you write cleaner, more efficient, and reliable code in C++. Happy coding! Welcome to today's tutorial on C++ Move Semantics, an essential concept that optimizes performance in your applications. In this video, we will explore how Move Semantics allow us to transfer ownership of resources rather than copy them, which can significantly enhance efficiency in certain scenarios, particularly with dynamic memory management. So far, we covered the importance of managing memory leaks and resource allocation in C++, emphasizing the necessity of pairing new with delete to avoid memory leaks. We explored the impact of exceptions on memory management and how RAII can mitigate risks associated with dynamic memory. Additionally, we delved into smart pointers such as STD, unique PTR, and STD, shared PTR, which automate memory management and help prevent leaks. Overall, effective memory management is crucial for developing reliable and efficient applications in C++. Now, we will talk about Move Semantics, a technique that greatly enhances how we handle resource management. Now let's take a look at our buffer class implementation, which serves as a solid example of move semantics in action. This class manages a dynamic array, initializing its resources using a constructor that allocates memory based on the specified size. Next, we implement the move constructor, which allows the efficient transfer of ownership from one buffer instance to another. When we instantiate buff2 using std, move buff1, the move constructor is invoked, transferring the data pointer and size from buff1 to buff2. After this transfer, buff1's data pointer is set to nullter, ensuring it doesn't attempt to delete the memory it no longer owns. This design avoids double deletion, preserving memory integrity. Additionally, we implement a destructor to release the allocated memory when a buffer object goes out of scope, thus preventing memory leaks. When executed, this example demonstrates how move semantics reduce overhead by eliminating unnecessary copying. Following this, we will see how move operations can be applied within a container like std vector, further illustrating the efficiency gains achieved through move semantics. Now let's take a look at an extended version of the buffer class that further demonstrates move semantics by incorporating both a move constructor and a move assignment operator. This class manages dynamic memory for an integer array, showcasing how to transfer ownership effectively. In this implementation, the constructor allocates memory for the buffer, and we display a message indicating the buffer's size. The move constructor is particularly important as it takes an R-value reference to another buffer instance. Here, we transfer the resource pointer from the source object, other, to the target object, ensuring that we take control of the memory without duplicating it. After this transfer, we nullify the source's data pointer to avoid double deletion, preventing undefined behavior. Next, we implement the move assignment operator, which operates similarly to the move constructor, but allows us to assign one buffer to another after first releasing any existing memory owned by the target. This process mirrors the move constructor's logic, ensuring that resources are managed efficiently throughout their life cycle. Finally, in the main function, we create a vector of buffer objects, showing how we can effectively utilize move semantics when adding temporary buffers into the vector. Through this approach, we optimize performance by avoiding unnecessary copies. The horizontal bar chart titled Efficiency of Memory Management Techniques in C++ displays 4 techniques on the vertical axis: traditional copy, move semantics, RAII, and smart pointers, against a horizontal axis labeled performance efficiency %. The plotted values are traditional copy at 10%, move semantics at 80%, RAII at 70%, and smart pointers at 60%. Key patterns are immediately visible. Move semantics leads by a wide margin, indicating it provides the highest measured performance efficiency among the 4 techniques. RAII follows closely behind move semantics with a 70% efficiency, showing that deterministic resource management yields strong performance benefits as well. Smart pointers register a solid but lower efficiency at 60%, suggesting that the safety and convenience they provide come with a modest runtime or management overhead compared to raw move operations or RAII idioms. Traditional copy sits at only 10%, highlighting that copying resources is drastically less efficient in scenarios where moving or ownership transfer is feasible. From these values, we can conclude that preferring move semantics for expensive-to-copy resources yields the greatest performance gain, while RAII and smart pointers remain valuable patterns that balance safety and efficiency. RAII being nearly as efficient as moves, and smart pointers trading some efficiency for automated lifetime management. Now let's take a look at a practical implementation of move semantics using std, unique PTR. In this example, we define a resource class that utilizes a std, unique PTR int to manage a dynamically allocated integer. The constructor initializes the unique pointer, safely allocating memory and setting its value to 42. Next, we implement a move constructor for the resource class, which efficiently transfers ownership of the unique PTR from one resource instance to another. When the move constructor is invoked, it uses std, move on the other resource, thereby transferring the underlying pointer while leaving other in a valid but unspecified state. This ensures that the original object does not own the resource anymore, preventing potential double deletes and optimizing memory management. In the main function, we create an instance of resource, then call its showResource method to display the value it holds. Following that, we utilize std, move to transfer ownership of raise1 to raise2. After the move, calling showResource on raise2 confirms the successful transfer, demonstrating the strength and efficiency of move semantics combined with smart pointers for proper resource management in C++. Now let's take a look at a practical implementation of move semantics using the std exchange function. We start by defining a class named container, which manages an integer pointer, data. The class constructor initializes data by dynamically allocating an integer. In the destructor, we ensure to properly release the allocated memory to prevent leaks. Next, we have the setValue method, which replaces the current value of data with a new integer value passed as an argument. Here, the beauty of std exchange comes into play. It not only assigns the new value to data, but also returns the previously held value. This allows easy access to the old value before it gets replaced, making it efficient and intuitive to work with the resource. The showValue method is straightforward as it simply outputs the current value stored in data. In the main function, we create an instance of container initialized with the value 10. We display this value, then call setValue to update data to 20 and again show the updated value. This illustrates how we can easily manage and update resources with minimal overhead, showcasing the power of move semantics and the utility of std exchange. By utilizing move semantics alongside utility functions like std exchange, you can write more expressive and efficient resource management code. Understanding when to use moves instead of copies helps you circumvent unnecessary overhead, leading to applications that are performant and responsive. In conclusion, move semantics in C++ represent a paradigm shift in memory management, allowing developers to write more efficient and expressive code. We've covered how to implement move constructors and assignment operators, how to use smart pointers like std, unique PTR, and streamlined operations with std exchange. Applying these concepts will equip you with the tools necessary to enhance your C++ applications significantly by optimizing performance and resource management. Thank you for tuning in. Make sure to practice these concepts in your own C++ projects, and happy coding. Understanding object size and padding in C++ is essential for grasping how data is stored in memory and the implications of data alignment on performance. Storage efficiency and memory usage are critical considerations in application development, especially regarding resource-heavy tasks such as graphics processing or data manipulation. Today, we will dive deep into the mechanics of object size, its calculation, and how padding impacts it. So far, we learned about C++ move semantics, a technique that optimizes resource management by transferring ownership of resources instead of copying them, enhancing performance particularly in dynamic memory scenarios. We discussed the implementation of move constructors and assignment operators, alongside the importance of using smart pointers to automate memory management and prevent leaks. Additionally, we explored utilities like std exchange that facilitate efficient value management. Understanding and applying these concepts are crucial for writing efficient C++ applications. Now we'll cover how object size is determined in C++, the role of padding in this process, and how these concepts influence memory layout and performance. Now let's take a look at a practical example of a struct in C++. The struct example contains three data members, a char type named A, an int type named B, and a short type named C. Upon defining this struct, we see how different data types contribute to the total size of the object, which is crucial for understanding memory layout in C++. The char occupies 1 byte, the int typically requires 4 bytes, and the short takes up 2 bytes. However, this seemingly adds up to 7 bytes, which is where the concept of padding comes into play. Next, we will write a simple main function that calculates the size of our example struct using the sizeof operator. This operator allows us to observe the actual memory size the struct occupies, including any additional padding added by the compiler for alignment purposes. When the program is executed, we will discover that the output reveals a size of 12 bytes, thus illustrating how padding can inflate the memory usage beyond the straightforward addition of the individual member sizes. This understanding is vital for efficient memory management in C++. Let's explore how to create a simple struct in C++ and analyze its size. We define a struct named example, comprised of 3 data members, a character A, an integer B, and a short integer C. The memory allocation for these members is as follows. A uses 1 byte, B, being an integer, typically occupies 4 bytes, and C, as a short integer takes 2 bytes. In the main function, we apply the sizeof operator to determine the total size of the example struct. Upon running the program, the output reveals size of example, 12 bytes. This total size illustrates more than just the addition of the individual member sizes. It also accounts for padding added by the compiler for alignment reasons. Specifically, you will observe that 3 bytes of padding are added after A to align B at a multiple of 4 bytes. Furthermore, the compiler includes an additional 2 bytes of padding after C to ensure that the entire size of the struct remains aligned with its largest member, which is B. This highlights the essential role of padding in memory layout for optimizing performance in C++. The displayed figure is a pie chart titled Impact of Padding on Object Size in C++ that breaks a hypothetical object allocation into 2 labeled slices, struct example with a value of 12 and padding effect with a value of 4. Visually, the chart shows the struct's useful data occupying 3/4 of the pie, 75%, and padding occupying 1/4, 25%. From these displayed values and the percentages, the clear pattern is that padding can represent a sizable fraction of the total allocation. Here, 4 bytes of padding relative to 12 bytes of actual member storage. The conclusion to draw for the lesson is explicit. Padding is not negligible and can meaningfully inflate memory usage. This visualization reinforces the practical implications already discussed. Reordering members, choosing smaller types where appropriate, or using packing pragmas will change the relative sizes shown in such a chart. In other words, the chart quantifies the overhead that alignment rules introduce and underscores why careful struct layout matters when minimizing memory footprint and optimizing cache utilization. Now let's see how we can implement a demonstration of object size and padding using inheritance in C++. The code defines a base struct named base, which contains 2 members, an integer and a character. Following this, we define a derived struct called derived, which extends base by adding an additional double member. This inheritance relationship allows us to explore how the size of derived is influenced not only by its own members, but also by the members of its base class. In the main function, we use the sizeof operator to output the sizes of both the base and derived structs. This is crucial for understanding the combined memory footprint that includes not just member variables, but also any padding introduced by the compiler for alignment purposes. When executed, the program will display the total size of each struct, illustrating how the presence of inherited members and the need for proper alignment can surprise us with total sizes that are larger than merely the sum of their parts. This hands-on example provides a clear insight into inheritance-related padding and object sizing in C++, underscoring why these concepts matter in efficient memory management. Now let's see how we can implement a packed structure to better understand the effects of padding on object size. In this code, we begin by including the necessary headers, which enable us to use standard input-output functions and the size-related capabilities of C++. Next, we use the pragma pack push1 directive to control the alignment of the members in our structure, forcing the compiler to allocate memory for each member without inserting any padding between them. The packed example structure contains a character, an integer, and a short, respectively occupying 1, 4, and 2 bytes. With the packing alignment set to 1 byte, these members are arranged sequentially, resulting in the total size reflecting just their combined sizes, only 7 bytes. Finally, the main function prints the size of packed example, demonstrating that this struct, with its packed members, utilizes memory more efficiently. This example powerfully illustrates how adjustments to data alignment can lead to significant differences in memory layout, emphasizing the need for careful consideration of both storage efficiency and potential performance impacts due to misalignments. Now let's take a look at how nested structures work in C++ and their implications for object size and padding. The first code snippet defines an inner struct that contains a char and a double. Here, we note that the char, which typically occupies 1 byte, and the double, which usually requires 8 bytes, have different alignment requirements. When we define another struct, outer, that contains an instance of inner and an additional char, the compiler must align the data members appropriately, likely introducing extra padding for the double in inner and the inner instance within outer. Next, we will write a simple main function that outputs the sizes of both the inner and outer structs using the sizeof operator. This will help us illustrate how padding influences the overall size of these structures. Running this code allows us to examine the memory layout and see how the compiler's padding decisions result in a larger size than one might intuitively expect, highlighting the importance of understanding these concepts for efficient memory utilization in C++ applications. As you can see, navigating through the object size and padding landscape in C++ requires a clear understanding of how types align in memory. It's crucial to adopt an approach where performance considerations due to padding or misalignment penalties are weighed against memory usage efficiency. Knowing when to apply specific structures, how packing works, and recognizing the importance of alignment makes you a better C++ developer overall. Before we wrap up, let's summarize what we've discussed. We've examined how the size of an object is calculated in C++, the role of padding in influencing this size, and how these factors affect inheritance and user-defined types. We also explored techniques for controlling padding and packing to observe its effects directly. C++ offers remarkable flexibility in managing memory, but with that comes the requirement for diligence in understanding how data is represented within that memory. This knowledge empowers you to write applications that not only function correctly, but also perform efficiently. Thank you for joining this discussion on understanding object size and padding in C++. Being mindful of these aspects of memory can influence your C++ programming journey significantly. So remember, being conscious of how your structures are laid out in memory will serve you immensely in mastering not just C++, but overall programming practices. Happy coding! Understanding object lifetime in C++ is crucial for managing memory effectively and ensuring efficient application performance. In this video, we'll dive deep into the topic of automatic objects and their destruction at the end of their scope, shedding light on the well-defined order in which this occurs. So far, we learned about the importance of understanding object size and padding in C++, which directly affects memory consumption and performance. We discussed how the size of an object is determined by the sum of its non-static data members and any padding added by the compiler for alignment. Additionally, we covered how padding can significantly inflate the size of objects, especially in cases of struct inheritance and user-defined types. Techniques for controlling padding and packing were also explored, highlighting their impact on memory layout and access speed. Now we will talk about object lifetime, how automatic objects are managed, and their scope in C++. Now let's take a look at a practical example demonstrating the concept of automatic objects in C++. In this code, we define a class called example, which includes a constructor and a destructor. The constructor automatically outputs a message when an instance of example is created, signaling the commencement of its lifetime, while the destructor outputs a message when the object is destroyed, marking the end of its lifetime. Next, we implement the function createObject, where we declare an instance of example named obj. Since obj is an automatic object, it is created when createObject is called, and it will be automatically destructed when the function scope exits. This exemplifies how automatic object management works in C++. Finally, the main function calls createObject, and after the function finishes executing, we see a message confirming that the object has been created and destroyed within the scope. This illustrates the effective lifecycle management of automatic objects in C++ and highlights the importance of scope in resource management, ensuring that no manual deallocation is needed and preventing memory leaks. Now we'll explore a practical example that demonstrates the concept of scope and object lifetime in C++. Here we define a class named data, which includes a constructor and a destructor. The constructor outputs a message when a data object is created, indicating its initialization with a specific value. Conversely, the destructor similarly outputs a message upon the object's destruction, providing insight into when the memory allocated for that object is reclaimed. Next, we implement a main function that contains nested blocks, showcasing how object lifetimes are scoped. Within the outer block, we create an instance of data named which exists throughout the duration of that block. Inside this block, we have another nested block where B is instantiated. Upon exiting the nested block, B is destructed first, exemplifying the last in first out principle. Once we finish the outer block, is destructed thereafter. This structured destruction process not only highlights the importance of scope in C++, but also epitomizes effective resource management, reinforcing how C++ handles automatic objects efficiently and safely. Now let's take a look at a practical example demonstrating the management of automatic objects using a vector. In this code, we define a class named element, which has a constructor and a destructor that output messages indicating when an object is constructed and destructed, respectively. This provides clear feedback about the life cycle of element objects. Next, we create a std vector to hold instances of the element class. The method implaceBack is employed to directly construct each element inside the vector, allowing us to add elements while managing their lifetime seamlessly. As new elements are added to the vector, they occupy a contiguous memory space, enhancing data access efficiency. When the main function concludes, the vector itself goes out of scope, triggering the automatic destruction of all element objects contained within. This happens in the reverse order of their construction, showcasing the last in, first out LIFO nature of destructors. By relying on C++ automatic management, we ensure that resources are freed correctly without requiring explicit deletion, effectively minimizing the risk of memory leaks and promoting robust resource management practices in our applications. The displayed bar chart titled Understanding Object Lifetime in C++ compares the relative importance assigned to 4 key concepts: automatic objects 70%, dynamic objects 30%, memory leaks 20%, and resource management 90%. Each bar is labeled with its percentage value, so the chart immediately communicates that resource management is emphasized far above the others 90%, followed by automatic objects at a substantial 70%. Dynamic objects register at 30%, indicating a moderate focus, while memory leaks appear at 20%, the lowest of the 4. From these values, we can conclude that the lesson prioritizes correct and robust resource handling, reflected by the top score for resource management, highlights stack-based automatic lifetime management as a primary mechanism, 70% for automatic objects, and treats raw dynamic allocation and the risk of leaks as lesser but still relevant concerns, which supports the push towards safer practices like smart pointers, RAII, and careful ownership semantics discussed elsewhere in the lesson. Now let's take a look at how we can implement a class that manages a dynamic array while adhering to the rule of 3. The dynamic array class dynamically allocates memory for an array of integers, with its constructor allocating the specified size and printing a message to indicate successful construction. Next, we define a destructor that ensures the allocated memory is properly released, thereby preventing memory leaks when the object goes out of scope. This ensures that the program cleans up resources automatically. To comply with the rule of 3, we implement a copy constructor that creates a deep copy of another dynamic array instance. This means that when an object is copied, it allocates new memory and copies the contents from the original, ensuring both objects manage their own separate memory without conflict. We also implement the copy assignment operator to handle assignment between 2 dynamic array instances safely. It checks for self-assignment, deletes any existing data to avoid memory leaks, and then allocates new memory similar to the copy constructor. Finally, the main function illustrates the usage of this class, demonstrating how the copy constructor and assignment operator are triggered, thereby reinforcing the importance of proper resource management in C++. Now let's take a look at how we can effectively manage object lifetimes in C++ using smart pointers. In this example, we define a class named SmartElement, which has a constructor and a destructor that output messages when an object is created and destroyed, respectively. This provides clear feedback on the object's life cycle, demonstrating how C++ handles object creation and destruction. Next, we implement the main function where we create a std, unique PTR to manage the memory of SmartElement. By using std, make unique, we ensure that the memory allocated for SmartElement is automatically cleaned up when the unique PTR goes out of scope. This means there's no need for explicit memory management with delete, reducing the risk of memory leaks. As soon as the scope of the main function ends, the std, unique PTR will automatically invoke the destructor of SmartElement, ensuring that resources are released properly. This showcases the power of smart pointers introduced in C++11, emphasizing the ease of managing dynamic memory without the burden of manual intervention, ultimately making our code cleaner and safer. In conclusion, understanding the lifetime of objects in C++ is imperative for writing efficient and bug-free code. By utilizing automatic objects and adhering to best practices such as the rule of three and leveraging smart pointers, you can prevent common issues related to resource management in C++. Always remember, a well-managed object lifecycle leads to less clutter in your code and a lot more fun while you're coding. So next time you define an object, think about its lifetime and let C++ handle the cleanup while you focus on crafting elegant solutions. Thanks for tuning in and happy coding. In this lesson, we're diving into advanced resource management techniques in C++, focusing on the scenarios where a class explicitly manages resources. We're going to explore how the default-generated special functions often fall short and what you can do to enhance resource management in your applications. So far, we learned about object lifetime in C++, emphasizing the difference between automatic and dynamically allocated objects. We discussed how automatic objects are created and destructed within their block scope, reducing the risk of memory leaks. The order of destruction follows a specific pattern, which is crucial for effective resource management. Lastly, we explored the rule of three and the use of smart pointers to ensure safe memory practices. Now we will cover more advanced techniques that help ensure that resource management is robust, especially when writing classes that manage dynamic resources like memory, file handles, or network sockets. The displayed figure, titled Key Concepts in Advanced Resource Management Techniques in C++, is a horizontal bar chart that quantifies the relative importance of four topics: resource management 90%, smart pointers 80%, exception safety 75%, and move semantics 65%. The y-axis lists the key concepts, while the x-axis shows importance as a percentage from 0 to 100, and each bar has its percentage value annotated at the bar end: 90%, 80%, 75%, 65%. The clear pattern is that resource management ranks highest, indicating it is the foundational concern. Smart pointers are the next most emphasized, reflecting their central role in safe ownership and lifetime management. Exception safety is substantial but slightly lower, highlighting the necessity of robust error handling guarantees such as the copy and swap idiom. And move semantics, while still important, is shown with a lower percentage than the other items, suggesting it is primarily an optimization tool to improve efficiency once correct ownership and exception safety practices are in place. From this visualization, we can conclude a recommended prioritization when designing classes. First, ensure correct resource ownership and overall resource management strategies, then adopt smart pointers to simplify ownership, build strong exception safety guarantees, and finally apply move semantics to optimize performance without compromising correctness. Now let's take a look at how we can implement a class that effectively manages a dynamic array of integers, showcasing both copy and move semantics. We start by defining the dynamic array class, which contains a constructor for initializing the array with a specified size, along with a destructor that ensures proper resource deallocation. This is crucial as it prevents memory leaks. Next, we define a copy constructor that allocates new memory and copies the data from another instance, ensuring that each object manages its own resources independently. In contrast, the move constructor is designed for efficiency. It transfers ownership of the data from a source object while nullifying the source's pointer to prevent double deletion when both objects go out of scope. Additionally, we implement copy and move assignment operators. The copy assignment operator first checks for self-assignment before cleaning up existing resources, while the move assignment operator similarly transfers ownership and ensures that the moved from object is left in a safe state. Finally, in the main function, we demonstrate how to create instances and use move semantics to optimize resource management, all while maintaining correctness and safety in our application. Now let's take a look at how we can implement strong exception safety in our resource management class using the copy and swap idiom. In this example, we define a resource class that manages a dynamic array of integers where the constructor allocates the required memory and the destructor appropriately deallocates it to prevent memory leaks. Next, notice the copy constructor, which creates a copy of the resource from another resource instance by allocating new memory and copying the contents. This ensures that each object has its own copy of the data. The key part of this design is the copy assignment operator, which takes its parameter by value. By doing this, we can utilize the copy constructor to create a temporary copy, leaving the original object unchanged if an exception occurs during copying. The operator then employs the std swap function to efficiently exchange the resource members with those of the temporary object, simplifying resource management without complex error handling. This approach allows the program to uphold strong exception safety guarantees, ensuring that resources are safely deallocated and our class remains in a consistent state even in the event of an exception. Next, we will write a class called FileHandler that demonstrates effective management of non-memory resources, specifically file handles. In the constructor, we open a specified file and check if it opens successfully. If not, we throw a runtime error to avoid proceeding with an invalid state. This ensures that our program fails fast, making it easier to debug issues related to file handling. The destructor is designed to automatically close the file when the file handler object goes out of scope, safeguarding against resource leaks. This is a vital part of resource management since it ensures that we are not leaving open file handles, which can lead to undefined behavior or application crashes. Additionally, the write function provides a controlled mechanism for writing data to the file, checking first if the file is still open. By enforcing this check, we add another layer of safety to our resource management practices. This approach highlights the importance of implementing RAII, resource acquisition is initialization, principles, thereby ensuring that resources are allocated and released appropriately, leading to robust and maintainable code. Now let's take a look at a simple custom vector implementation, which mimics the behavior of std vector in C++. This custom vector class starts with an initial capacity of 1 and employs a strategy to double its capacity whenever it becomes full, ensuring efficient memory usage as elements are added. In the implementation, the constructor initializes the vector's size and allocates memory for the data. The important memory management occurs in the private resize method, where a new larger array is created and existing elements are copied over. This prevents potential memory issues by dynamically adjusting to the number of stored elements. The pushback method allows users to add integers to the vector. It checks whether the current size exceeds the capacity, triggering a resize if necessary. Meanwhile, the operator overload provides safe access to elements, throwing an exception if an out-of-bounds index is used. Lastly, the destructor ensures that all dynamically allocated memory is released when the vector goes out of scope, preventing memory leaks and reinforcing good resource management practices. In conclusion, mastering advanced resource management techniques is essential for creating robust and efficient applications in C++. Understanding copy and move semantics allows you to optimize the handling of resources, while exception safety practices ensure your code remains stable even under error conditions. Whether you're managing dynamic memory or non-memory resources, knowing how to implement the rule of 5, adding move constructors and move assignment operators, along with best practices for handling exceptions can save you from common pitfalls. As you continue your journey in C++, keep this knowledge in your toolkit. Remember always to think about how your classes manage resources and be proactive in avoiding leaks and inconsistencies. Happy coding, and get ready to tackle even more exciting challenges ahead. In today's lesson, we're diving deep into implementing custom deleters in C++, paying special attention to the rule of 3. This rule is essential for managing resources effectively, ensuring that our objects handle their memory and other resources with care. So far, we learned about advanced resource management techniques in C++, focusing on object lifetime and the differences between automatic and dynamically allocated objects to prevent memory leaks. We covered the rule of 3 and the importance of smart pointers, along with copy and move semantics for efficiently transferring resources. Exception safety was introduced, emphasizing the copy and swap idiom for ensuring stability during resource management when exceptions arise. Additionally, we touched on managing non-memory resources and the importance of implementing robust techniques for managing larger data structures or container classes. Now we will talk about how to effectively implement custom deleters, along with the necessary copy operations like copy constructor and copy assignment. Now let's take a look at the dynamic array class, which effectively demonstrates the rule of 3 in action. This class manages a dynamically allocated integer array and introduces essential functionalities for resource management. It begins with a constructor that allocates memory for the array based on the specified size. This allocation is crucial, as it lays the foundation for the array's use. Next, we have the custom destructor, which plays a vital role in freeing the allocated memory when the object goes out of scope. If we were to omit this destructor, we would encounter memory leaks, leading to inefficient resource usage over time. Then we implement the copy constructor, crucial for deep copying objects to prevent multiple instances from sharing the same memory address, a common pitfall that leads to dangling pointers. Finally, the copy assignment operator ensures that existing resources are safely released before copying new data, handling self-assignment effectively. By writing this operator, we guarantee that the dynamic array manages resources correctly and safely, fulfilling its contract as a container managing dynamic memory. This meticulous approach to resource management helps prevent issues that can compromise application stability. Next, we have our copy constructor, which is crucial for creating deep copies of our dynamic array objects. If we simply did member-wise copying, which would happen if we did not define this constructor, both objects would end up pointing to the same array in memory. When one goes out of scope and the destructor is called, the memory would be freed, leaving the other object with a dangling pointer. This creates undefined behavior and is generally something you want to avoid like a bad joke. In the copy assignment operator, we add additional safety by checking for self-assignment. If we are trying to assign an object to itself, we let it return without doing anything further. Otherwise, we must first clean up the existing data by releasing the memory and allocate new resources for the incoming data. Utilizing functions like std, mempy helps in efficiently copying the bits of the data over to the new allocation. However, you might wonder, all of this might seem like a lot of boilerplate code. Luckily, C++ offers a more elegant solution using smart pointers, which automatically handle resource management, thereby reducing the chances of memory leaks. Nevertheless, understanding how to manually manage resources prepares you better for using smart pointers efficiently. The displayed chart titled Key Concepts in Resource Management in C++ maps 5 concepts on the x-axis: destructor, copy constructor, copy assignment, smart pointer, and exception safety, to their numeric importance levels on the y-axis. From the bar heights and the numeric labels shown atop each bar, copy assignment and exception safety both register at the maximum value of 5, indicating they are considered the top priorities in this representation. Destructor and smart pointer each have a value of 4, showing they are rated highly but just below the top tier. The copy constructor is assigned a value of 3, making it the least emphasized of the 5 in this view. The explicit numeric annotations on each bar make these relative priorities unambiguous. Highest emphasis is placed on ensuring safe assignment semantics and robust exception handling, while destructors and smart pointers remain critical supports, and the copy constructor is important but comparatively less emphasized. This breakdown reinforces the lesson's focus. While proper destruction and smart pointer use are essential, guaranteeing safe copying assignment behavior and exception safety are the most critical concerns when managing resources. Now let's implement a custom deleter alongside our class, providing flexibility in resource management beyond basic memory control. In the custom deleter array class, we create a member variable to hold a pointer to dynamically allocated memory, along with a size variable to track the number of elements. The constructor takes 2 parameters, the desired size and a std function that will define how to release the resource when the object is destroyed. This allows us to specify custom behavior in the event of deletion, making our class adaptable for various resource types. In the destructor, instead of using the conventional delete operator, we call the custom deleter. This ensures that whether we're simply deleting an array or need to perform additional cleanup tasks, we have the means to handle it gracefully. To demonstrate this, we define a custom delete function that encapsulates the logic for deleting the allocated memory and outputs a message confirming the action. Next, we see how to utilize this class by creating an instance of custom deleter array and passing a lambda function as the custom deleter. This lambda not only performs the deletion, but also logs a message, showcasing the practical benefits of using custom deleters in managing resources efficiently and flexibly. Now let's see how we can implement the custom deleter array class, which enhances our resource management capabilities in C++. In this example, we create a custom deleter array that accepts a size and a custom deleter function. The constructor allocates memory for an integer array and takes a function that defines how this memory will be released upon destruction. The destructor then utilizes this custom deleter instead of the standard memory release procedure. This approach grants us flexibility, allowing us to incorporate specialized actions during resource cleanup, such as logging information or closing files, making our resource management strategies more robust. Next, let's use this class in a practical scenario with the main function. We define a lambda expression that serves as our custom deleter, which outputs a message indicating that the array is being deleted before actually freeing the memory. By creating an instance of custom deleter array, we trigger the custom deleter when the array goes out of scope, showcasing how this feature can be utilized to enhance debugging and overall resource management in our applications. This illustrates the power of custom deleters in C++ when handling complex resources. Understanding the rule of 3 leads us to another concept, the rule of 5, which comes into play with modern C++. It expands upon the rule of 3 by including move semantics, the move constructor, and move assignment operator. When dealing with resource management in C++, it's vital to learn when and how to utilize these tools effectively, as they optimize performance by allowing the transfer of resources rather than copying. I encourage you to explore these features as they are fundamentally tied to performance improvements you can deliver in your code. However, that's a topic for another day. Make sure to practice writing classes and managing resources using the techniques we covered today. In summary, we explored the rule of 3, implementing destructors, copy constructors, and copy assignment operators to ensure robust memory management in C++. We then introduced custom deleters, showcasing how they enhance flexibility in resource management. Practice implementing these patterns in your projects, and you'll develop a much deeper understanding of C++ memory management capabilities. Stay tuned and happy coding. In today's lesson, we will explore smart pointers, a powerful feature in C++ that simplifies memory management by automatically managing resource allocation and deallocation. So far, we learned about the implementation of custom deleters in C++ and the importance of the rule of 3 for effective resource management. We discussed the risks associated with default implementations of destructors, copy constructors, and copy assignment operators, highlighting the necessity for careful memory handling. The concept of custom deleters was introduced to manage resources beyond memory, emphasizing their flexibility and potential for enhanced resource management. Lastly, we touched on the rule of 5, which includes move semantics for optimizing performance in modern C++. Now we will dive into smart pointers and see how to utilize them effectively to harness the benefits of automatic memory management in our applications. First, let's break down what smart pointers are and why they matter. Smart pointers are objects that act like pointers but provide additional functionalities such as automatic memory management. They help prevent memory leaks and dangling pointers, two common pitfalls in C++. In modern C++, there are three primary types of smart pointers: STD, unique PTR, STD, shared PTR, and STD, weak PTR. Each smart pointer serves a different purpose and is utilized in different scenarios, ensuring that your resource management is not only effective but also safe. The displayed figure, titled Smart Pointer Utilization in C++, is a grouped bar chart comparing two metrics across the three smart pointer types: an importance level, score, and usage frequency, %. For STD unique PTR, the chart shows an importance score of 9 and a usage frequency of 70%. For STD shared PTR, the importance score is 7 with a 50% usage frequency, and for STD weak PTR, the importance score is 5 with a 30% usage frequency. The legend distinguishes the two measures, and the x-axis labels list the three pointer types, while the y-axis is labeled scores/frequency. Value labels are displayed on top of each bar, making the exact numbers immediately visible. The key pattern is a consistent descending trend from STD unique PTR to STD weak PTR for both metrics. Higher perceived importance aligns with higher usage. This alignment supports the practical conclusion that STD unique PTR is both the most valued and most commonly used smart pointer. STD shared PTR is used and valued moderately when shared ownership is required, and STD weak PTR is less frequently used and rated lower in importance, reflecting its specialized role, typically to break reference cycles or provide non-owning references. The chart thus reinforces the lesson's guidance to prefer STD, unique PTR by default, adopt STD, shared PTR when sharing is necessary, and rely on STD, weak PTR primarily to avoid circular references. Now let's see how we can implement STD, unique PTR, to manage resource allocation effectively in our code. We start by including the necessary headers, IOStream for input-output operations, and memory to use smart pointers. Next, we define a simple class named Smartclass with a constructor and destructor that output messages to the console. This will help us visualize when our object is created and destroyed, demonstrating the automatic management features of STD, unique PTR. In the main function, we create a STD, unique PTR called PTR that takes ownership of a new Smartclass instance. What's important to highlight here is that when PTR goes out of scope at the end of the main function, it automatically deallocates the memory associated with the Smartclass object, calling its destructor without any manual intervention required. This showcases how STD, unique PTR, significantly reduces the risk of memory leaks while simplifying memory management tasks. By using STD, unique PTR, you can ensure that resources are handled correctly and efficiently, leading to cleaner and safer code practices in your applications. Now let's see how we can implement ownership transfer using STD, unique PTR. In this example, we define a class called Smartclass, which has a constructor and destructor that print messages to indicate when an object is created and destroyed. This helps us visualize the lifecycle of our object. Next, we introduce a function called transferOwnership, which takes a STD, unique PTR smart class as a parameter. This illustrates how ownership of the dynamically allocated smart class object can be transferred. In the main function, we create a STD, unique PTR named PTR1 that takes ownership of a new smart class instance. To transfer the ownership of PTR1 to the transferOwnership function, we use STD, move, which effectively converts PTR1 into an R value. After this operation, PTR1 is set to nullter, demonstrating that it no longer holds ownership of the object, thus preventing potential issues like double deletion. This showcases the safety and effectiveness of smart pointers in managing resource lifecycles, allowing us to maintain clean and efficient code. Now let's take a look at how to implement STD, shared PTR, which allows multiple pointers to share ownership of the same resource. In this example, we begin by including the necessary headers for input-output and memory management. Then we define a simple class named Smartclass, which has a constructor and a destructor that output messages when they are called. Next, we create an instance of STD, shared PTR named PTR1, initializing it with a new Smartclass object. This single pointer now manages the resource. We then delve into a block of code where we create another STD, shared PTR named PTR2, assigning it the same Smartclass instance that PTR1 points to. At this point, both pointers share ownership of the resource, which is illustrated by a message indicating that they are sharing ownership. When PTR2 goes out of scope, its reference count for the Smartclass instance decreases, but the object remains alive because PTR1 still owns it. Finally, as PTR1 exits the scope at the end of the main function, the destructor for Smartclass is called, freeing the memory automatically and demonstrating the seamless management of shared resources that STD, shared PTR, enables. Next, we will implement a simple example that demonstrates the concept of circular references between STD, shared PTR instances, and how to break this cycle using STD, weak PTR. In the code, we define a node class which contains a STD, shared PTR named Next, allowing each node to point to another node. Inside the main function, we create two instances of node managed by STD, shared PTR, node 1 and node 2. Initially, we establish a circular reference by assigning node 1 next to point to node 2 and node 2 next back to node 1. This situation can lead to memory leaks as the reference count will never reach 0 due to the cyclic ownership. To address this issue, we introduce a STD, weak PTR, which creates a non-owning reference to node 2 from node 1. Unlike STD, shared PTR, this weak reference does not affect the reference count of node 2. By resetting node 1 next, we break the cycle, allowing node 1 to be destroyed and preventing any memory leak. This example illustrates the importance of using STD, weak PTR, to manage dependencies effectively in data structures. As we have seen, by utilizing STD, unique PTR, STD, shared PTR, and STD, weak PTR, we can effectively manage dynamic memory and resources in our C++ applications while reducing the risk of memory leaks and undefined behavior. These smart pointers offer a cleaner, safer alternative to raw pointers, making your code easier to read and maintain. Let's recap some best practices to keep in mind. Always prefer STD, unique PTR, when you need single ownership. This will give you the benefit of automatic memory management with minimal overhead. Use STD, shared PTR, when multiple copies of a pointer need to share the same resource, and STD, weak PTR, to avoid circular references. Also be mindful that the overhead of managing reference counts with STD, shared PTR, can affect performance in scenarios requiring high efficiency, so choose the smart pointer that best fits your needs. In conclusion, smart pointers in C++ are a powerful tool for managing resources and ensuring memory safety by automatically handling resource allocation and deallocation. From STD, unique PTR for unique ownership, to STD, shared PTR for shared ownership, and STD, weak PTR, to prevent circular references, each type plays a critical role in effective memory management. Remember, embracing these smart pointers will not only help you avoid common pitfalls, but also enhance the overall robustness and clarity of your code. Keep experimenting and applying these concepts to your projects, and you'll find that memory management becomes significantly more manageable and less error-prone. Happy coding! In today's session, we will delve into advanced techniques in resource management, specifically focusing on the rule of 5 in modern C++ programming. This concept expands upon the traditional rule of 3 by incorporating two-move operations, facilitating more efficient resource management in your applications. So far, we covered smart pointers in C++, which significantly enhance memory management through automated resource allocation and deallocation. We've examined STD, unique PTR, STD, shared PTR, and STD, weak PTR, focusing on their use cases and their impact on memory safety. We also stressed the importance of preventing circular references and the criteria for choosing the right smart pointer for different scenarios. Our goal is to enhance code clarity and diminish the chances of encountering memory leaks. Now, let's talk about the rule of 5 and how it enhances our resource management in modern C++. The displayed pie chart titled Distribution of Smart Pointer Usage in Resource Management shows 3 categories and their relative shares: unique pointer 30%, shared pointer 50%, and weak pointer 20%. From these proportions, we can draw several key observations relevant to design decisions. First, shared ownership, represented by STD, shared PTR, dominates at half of the distribution, indicating that in many code bases the need to share resource ownership across multiple components is common. Second, exclusive ownership, STD, unique PTR, still represents a substantial portion, 30%, emphasizing that a significant number of resources are managed with clear single ownership semantics, a situation where move semantics and the rule of 5 are particularly effective for performance. Third, weak references, STD, weak PTR, account for a smaller but meaningful slice, 20%, highlighting their specific role in breaking ownership cycles or observing resources without extending lifetime. The chart thus suggests a typical strategy. Prefer unique PTR. When ownership is exclusive for efficiency, use shared PTR. When ownership must be shared, accepting the associated overhead and complexity, and employ weak PTR selectively to avoid circular references while enabling safe observation. These choices directly inform when to rely on move operations, deleted copy operations, or defaulted behavior in classes that manage such pointers. Now let's take a look at the buffer class, which encapsulates a dynamic array and demonstrates the rule of 5 in action. The constructor initializes the buffer by allocating memory for an array of integers using the new keyword, while also storing the size of the buffer. When a buffer object is destroyed, the destructor efficiently releases the allocated memory, preventing any memory leaks. Next, we have the copy constructor, designed to create a deep copy of the buffer object. It allocates new memory and copies the contents from the source buffer, ensuring that both objects are independent. Similarly, the copy assignment operator provides a way to assign one buffer to another, ensuring that any existing resources are freed before acquiring new ones. Moving on to the move operations, the move constructor allows for the efficient transfer of resources from a temporary buffer object, leaving the source in a valid state by nullifying its pointer. The move assignment operator applies the same principles, allowing existing resources to be reassigned without unnecessary allocations. This combination of constructors and operators greatly enhances performance by taking advantage of move semantics introduced in C++11. Now let's implement the process buffer function, which will demonstrate the efficiency of using move semantics with our buffer class. This function takes an R-value reference to a buffer as its parameter. By using buffer and end, we signal that we intend to accept a temporary buffer object, allowing the function to seamlessly acquire the resources without duplicating them. Within the function, we process the buffer by utilizing the getSize method, which retrieves the size of the buffer dynamically allocated. This design choice ensures that we do not engage in costly copy operations, thus illustrating one of the primary advantages of move semantics, performance optimization. When this function is called with a temporary buffer, the move constructor is triggered, swiftly transferring ownership of the underlying data to the function. This means the resources are transferred with minimal overhead, demonstrating how move semantics can significantly enhance performance in scenarios involving large data buffers. By employing this technique, we capitalize on the efficiency of memory management, showcasing the true power of modern C++ resource handling. Now let's take a look at how we can implement a resource handler class that utilizes smart pointers while adhering to the rule of 5 for effective resource management. This class encapsulates a buffer object using std, unique PTR, ensuring that memory is managed automatically and avoiding manual memory handling issues. The constructor of the resource handler initializes the buffer through std, make unique, which both allocates and constructs the buffer object. This ensures that the resource is properly allocated and associated with the resource handler. The destructor is defaulted, allowing the unique PTR to automatically clean up the underlying buffer when the resource handler is destroyed, preventing memory leaks. We also implement the move constructor and move assignment operator, which are essential for transferring ownership of the buffer efficiently without duplicating it. These operations use std, move to transfer the unique PTR, allowing a new resource handler to take control of the resource while leaving the original in a valid state. The copy constructor and copy assignment operator are deleted to prevent unintended copying of the resource handler, which could lead to multiple unique pointers managing the same resource. Through this design, we maintain clear ownership semantics while leveraging the benefits of automatic resource management with smart pointers, illustrating the powerful combination of smart pointers and the rule of 5. Now let's see how we can implement the example class, which showcases the application of move semantics aligned with the rule of 5 principles. In this design, the class has a simple member variable, value, which is initialized through its constructor. Next, we introduce the move constructor, which facilitates efficient resource transfers by taking an R-value reference of another example object. Upon invoking this constructor, we transfer the ownership of the value from the given object and set the original object's value to 0, ensuring it remains in a valid state without retaining its original resources. Following this, we define the move assignment operator that performs similar operations when assigning one example object to another. This operator checks for self-assignment and transfers the value, resetting the source object's state as before. Finally, we demonstrate how example objects can be effectively utilized within an std vector. By reserving sufficient space in the vector beforehand, we optimize memory allocations and leverage in placeback to construct the example objects directly, triggering the move constructor for low overhead object management, enhancing both performance and efficiency in our application. In conclusion, mastering advanced techniques in resource management through the rule of 5 in C++ can greatly enhance both performance and resource safety in your applications. By implementing all 5 operations, you ensure that you're handling your resources with care, whether they're dynamically allocated or encapsulated within smart pointers. We've covered the structure of a class following the rule of 5, how to implement move semantics and the integration of smart pointers. You should now feel confident applying these techniques in your programming endeavors to achieve more robust and efficient C++ code. Remember, proper resource management is not just about freeing memory, but doing so safely and efficiently, allowing you to focus on what truly matters in your code, solving problems, and implementing your solution effectively. Don't forget to practice these concepts, try building your own classes following the rule of 5, and observe the differences in performance and safety. Happy coding! In this lesson, we are going to dive deep into the world of smart pointers in C++. Smart pointers are a crucial part of C++ memory management that enhance our programming practices by automating resource management and preventing common pitfalls like memory leaks. So far, we learned about advanced techniques in resource management in C++, specifically the rule of 5, which optimizes resource handling by incorporating move semantics. We discussed the importance of smart pointers for memory management and examined their types, focusing on their ownership semantics and use cases. Additionally, we explored how implementing the rule of 5 within custom classes, like buffer and resource handler, enhances performance and prevents memory leaks. Lastly, we highlighted practical examples illustrating the benefits of combining smart pointers with move semantics in real-world applications. Now, we will cover how to utilize smart pointer abstractions effectively to manage resources in our C++ applications. Smart pointers come in 4 primary types: STD, unique PTR, STD, shared PTR, STD, weak PTR, and there's also void asterisk, which can function as a generic pointer type. Unlike raw pointers, smart pointers provide a layer of abstraction that helps you manage dynamic resources in a safer, more efficient manner. Let's break down each of these pointer types to understand their uses better. Now let's take a look at how we can effectively use STD, unique PTR, to manage dynamic memory in C++. In our example, we define a function called processArray, where we create a STD, unique PTR named ArrayPTR to manage a dynamically allocated array of integers. By using STD, unique PTR, we ensure that the array's memory will be automatically released once ArrayPTR goes out of scope, which occurs at the end of the processArray function. Within the function, we use a loop to initialize the elements of the array, assigning each index a value that is 10 times its index. After initializing the array, we employ another loop to print each element to the console, demonstrating the array's contents to the user. This showcases the key benefits of STD, unique PTR. Not only does it simplify memory management by removing the need for manual deletion, but it also leads to clearer and safer code. By the time processArray completes, ArrayPTR is automatically destroyed, ensuring that the memory allocated for the array is properly released, preventing potential memory leaks. Now let's see how we can implement STD, shared PTR, to manage shared ownership of a dynamically allocated resource. In this example, we first create a STD, shared PTR named P1, which is responsible for managing an integer allocated on the heap. This allows P1 to take ownership of that integer, holding the resource safely. Next, we introduce another STD, shared PTR named P2, and assign it the value of P1. This action ensures that both P1 and P2 share ownership of the same integer, illustrating the shared ownership semantics provided by STD, shared PTR. A key feature of shared pointers is their ability to maintain a reference count, which tracks how many shared PTRs point to the same resource. In the code, we utilize the useCount function to display the reference count, demonstrating that it increases to 2 when P2 is created and goes back to 1 when P2 goes out of scope. Finally, the integer will be automatically deleted when the last STD, shared PTR, P1, that references it is destroyed or reset. This self-managing behavior of STD, shared PTR, helps prevent memory leaks, making it an excellent choice for situations requiring shared ownership. The figure displays a grouped bar chart comparing advantages % and disadvantages % across 4 pointer categories: unique pointer, shared pointer, weak pointer, and void pointer. For each category, there are 2 bars: the advantages bar labeled advantages % and the disadvantages bar labeled disadvantages %, with numeric data labels shown above each bar. The specific values shown are: unique pointer, advantages 80%, disadvantages 20%. Shared pointer, advantages 60%, disadvantages 40%. Weak pointer advantages 40%, disadvantages 60%. Void pointer advantages 30%, disadvantages 70%. From these values, several clear patterns emerge. Unique pointers show the largest advantage to disadvantage gap, 80% versus 20%, indicating the strongest perceived benefit in exclusive ownership, automatic cleanup, and minimal overhead. Shared pointers sit in the middle, 60% versus 40%, reflecting useful shared ownership capabilities, but with measurable cost from reference counting and potential complexity. Weak pointers show a reversed balance, 40% advantage versus 60% disadvantage, which highlights that while they are essential to break cycles and provide non-owning references, they are inherently more limited and introduce additional handling, locking, and lifetime checks. Void pointers show the poorest balance, 30% versus 70%, emphasizing that their flexibility comes at a high cost in terms of safety and error proneness. The chart's comparative layout reinforces practical recommendations. Prefer STD, unique PTR. When exclusive ownership is appropriate, choose STD. Shared PTR. When shared ownership is necessary and you can accept reference count overhead, use STD. Weak PTR strategically to avoid cycles but recognize its extra management burden, and treat void asterisk as a last resort escape hatch rather than a default choice due to its high disadvantages in safety and maintainability. Now let's take a look at how we can effectively manage circular dependencies using STD, weak PTR. In this code, we have a simple class called node that contains an integer value in a STD, shared PTR named next to link to another node. This setup allows for the construction of a chain of nodes. Inside the create circular dependency function, we begin by creating a shared pointer, node1, pointing to a new node with a value of 1. Next, to prevent circular references that could lead to memory leaks, we introduce a STD, weak PTR, weak node, which is initialized from node1. This means that while weak node can safely reference node1, it does not increase the reference count. Within a new scope, we create another shared pointer, node2, linking node1 to it. Importantly, when we set node2 next, we use weak node lock to retrieve a shared pointer to node1 without affecting its life cycle. This approach ensures that even after node2 goes out of scope, node1 remains valid and cleanly gets deallocated, showcasing how STD, weak PTR, serves as a crucial tool in avoiding memory leaks in scenarios where circular dependencies might arise. Finally, we print the value of node1 to confirm it is still accessible. Now let's take a look at how we can implement a function to process generic data types using void asterisk. In this example, we define a function called processData that accepts a void asterisk pointer along with a type identifier. The flexibility of void allows us to point to various data types, but this flexibility comes with the necessity of type checking. Inside the processData function, we use the type identifier to determine whether we're working with an int or a double. If the identifier indicates that we have an integer, we cast the void asterisk pointer to an int asterisk using static cast and then dereference it to display the integer value. Similarly, if the type is a double, we perform a cast to a double asterisk and display its value. This approach showcases how we can leverage void asterisk for dynamic type handling, but it also highlights the risks associated with improper casting, which could lead to undefined behavior if we mistakenly interpret the data as the wrong type. In the main function, we define an integer and a double value, and we call processData with the addresses of these variables and their respective type identifiers. This demonstrates how void allows interaction with different data types while emphasizing the importance of careful management of type safety. As we wrap up our discussion on smart pointer abstractions, it's vital to highlight the importance of choosing the right pointer type for your needs. Use STD, unique PTR, when you require strict ownership semantics for single ownership without sharing. For shared ownership, STD, shared PTR, is ideal, but ensure you're mindful of potential memory overhead due to reference counting. Finally, STD, weak PTR, can help avoid circular references while allowing for temporary non-owning references to an object. Before we conclude, it's essential to emphasize that while smart pointers help manage resources, they also come with their own sets of complexities. Understanding each smart pointer's nuances, their life cycle, and the appropriate use cases will make you a more effective and safer C++ programmer. Leverage these abstractions to write cleaner code that avoids common memory management pitfalls. In essence, smart pointers enable us to write C++ programs that not only make our lives easier, but also foster safer and more maintainable code bases. The memory management challenges of earlier C++ versions have been significantly alleviated, and using smart pointers allows you to focus on what matters most, solving the problem at hand. Happy coding, and may your pointers always point in the right direction. Memory management in C++ is a critical topic, especially when dealing with dynamic memory allocation. Today, we're diving deep into advanced memory management techniques, focusing specifically on the rule of three. It's essential to ensure that our code is robust and avoids common pitfalls like memory leaks or dangling pointers. So far, we learned that smart pointers in C++ are essential for effective memory management by automating resource handling and preventing memory leaks. We explored the different types of smart pointers: STD, unique PTR, STD, shared PTR, and STD, weak PTR, each serving specific ownership semantics. The lesson emphasized the importance of using these abstractions appropriately to enhance programming practices while being mindful of their complexities. Ultimately, smart pointers help create safer and more maintainable C++ code bases. Now we will talk about how to implement the rule of three in our own custom classes, including the destructor and the copy operations, the copy constructor, and the copy assignment operator. The accompanying horizontal bar chart titled Performance of Different Memory Management Techniques in C++ shows 4 techniques on the vertical axis with their performance scores on the horizontal axis. Unique pointer 85%, shared pointer 75%, weak pointer 60%, and smart pointer 90%. From these values, the clear pattern is that the generic smart pointer bar registers the highest score at 90%, followed closely by unique pointer at 85%. Shared pointer sits noticeably lower at 75%, and weak pointer is the lowest at 60%. The data therefore suggests a performance ranking: smart pointer, unique pointer, shared pointer, weak pointer. A practical conclusion you can draw from this visualization is that, when raw performance is a primary concern, choosing smart pointer variants that imply exclusive ownership, represented here by unique pointer and the general smart pointer entry, tends to yield higher scores, whereas shared ownership semantics, shared pointer, and non-owning references, weak pointer, are associated with lower performance scores in this comparison. Keep these relative scores in mind when weighing the convenience and safety of automatic resource management against performance requirements in your designs. Now let's take a look at how we can implement the rule of three through our int array class. This class is designed to manage a dynamically allocated array of integers, ensuring proper memory handling. Initially, we define the class with a constructor that allocates memory for the array and initializes its elements to 0, which is crucial for avoiding uninitialized values. Next, we include a destructor that explicitly deletes the allocated memory when an object of int array goes out of scope, preventing memory leaks that can occur if we forget to release resources. Now let's examine the copy constructor. This is particularly important because it creates a new instance of the array with its own memory allocation when a new int array object is initialized using an existing one. This ensures that each object can independently maintain its data without risking shared pointers leading to issues. Lastly, the copy assignment operator checks for self-assignment and takes care to delete the existing array before allocating new memory and copying values. This approach guarantees robust memory management and avoids potential pitfalls like double deletions, showcasing a proper implementation of the rule of three in C++. Now let's break down each of these components further, starting with the constructor. This code initializes the int array class with a specific size and allocates memory accordingly, ensuring that we have a clean slate, everything set to 0. When you need an array of integers, you simply call the constructor, and it takes care of everything behind the scenes. Next, we look at the destructor. It's key for cleaning up resources. If we forget to free the allocated memory, we end up with a memory leak, which, in long-running applications, can lead to significant resource waste. The destructor effectively handles this by deleting the array when an object of int array goes out of scope. Now, the copy constructor can often be a bit tricky. This is where we ensure that each copy of an object gets its own separate memory allocation. If we simply copied the pointer from one object to another, we would face the risk of both objects trying to delete the same memory when they go out of scope. To prevent this, we create a new array, allocate memory, and then copy over the elements from the source array. The copy assignment operator is slightly more complex. It checks for self-assignment. This is to handle scenarios where an object is assigned to itself. We first delete the existing array to free up memory before we allocate again and copy the data. This prevents memory leaks and ensures we have fresh data in our new object. Now let's implement the following example to see the rule of 3 in action with the int array class. In this demonstration, we first create an instance of int array named r1 with a size of 5, initializing it to hold 5 integers. Calling the print method on r1 shows that all array elements are set to 0, confirming that our constructor works as intended. Next, we derive r2 from r1 using the copy constructor, which creates a distinct copy of the data in r1. After invoking r2 print, we see that it matches r1, demonstrating our successful deep copy implementation. Each array operates independently, so changes to one will not affect the other. Following this, we illustrate the copy assignment operator by reassigning r1 to a new int array instance of size 3. This action triggers the copy assignment operator, ensuring that any previously allocated memory in r1 is cleaned up to prevent memory leaks before the new values are copied. After calling r1 print, we see that it now reflects the new allocation, emphasizing the importance of proper memory management in C++. Now let's take a look at a simple implementation of a class called intArrayDefault that allocates a dynamic array. This class has a private member r, which is a pointer to an integer array, along with a size variable to track the number of elements in the array. The constructor initializes r using new, allocating the specified amount of memory based on the size provided when creating an object of this class. Next, we need to highlight that this class only includes a destructor, which properly deallocates the memory occupied by r to prevent memory leaks when an object goes out of scope. However, this implementation lacks a user-defined copy constructor and copy assignment operator. If you create multiple instances of intArrayDefault and attempt to copy or assign them, the default behavior of simply copying the pointer will lead to multiple instances trying to delete the same block of memory. This situation can cause undefined behavior, such as program crashes. Therefore, while this code may seem simpler at first glance, it emphasizes the importance of implementing the rule of 3 to ensure safe memory management in C++. In the next steps, we will learn how to add the necessary functionalities to avoid these pitfalls. In practice, understanding and implementing the rule of 3 is essential for maintaining memory safety in C++. The effort ensures that your classes are not only efficient but also reliable. As with many things in programming, a little foresight can save you from major headaches down the line. If you find that your classes need to work with copied data frequently, it might be beneficial down the road to consider implementing the rule of 5 by also including move semantics, which can optimize performance by transferring resource ownership. But that's a topic for another day. Remember, proper memory management is a foundational concept in C++. Even if we have wonderful abstractions provided by modern C++, understanding the underlying mechanics gives you an edge in writing cleaner, faster, and safer code. In conclusion, mastering the rule of 3 is a step towards becoming a proficient C++ programmer. You've learned how to implement the destructor, copy constructor, and copy assignment operator, and why they are crucial in managing memory correctly. Each component plays its role in ensuring that your dynamically allocated resources are handled correctly, preventing leaks and crashes. By grasping these concepts, you'll build a solid foundation that will aid you in writing high-quality code as you delve further into the exciting world of C++. Keep coding and happy learning. Move semantics is a powerful feature introduced in C++11 that allows for more efficient management of resources, particularly when it comes to dynamic memory allocation and object handling. In this lesson, we're going to explore what move semantics are and how they can significantly enhance the performance of your C++ programs. So far, we learned that effective memory management in C++ involves understanding the rule of 3, which requires implementing a user-defined destructor, copy constructor, and copy assignment operator to prevent issues like memory leaks. We explored how smart pointers such as std, unique PTR, std, shared PTR, and std weak PTR facilitates safer resource management. Additionally, we examine the implementation of these concepts through a custom int-array class, emphasizing the significance of deep copying. Ultimately, mastering these techniques ensures more robust and maintainable C++ code. Now, we will cover move semantics, which can optimize memory performance even further by allowing the transfer of resources instead of copying them. When we talk about move semantics, we are primarily focusing on the ability to transfer ownership of resources, such as dynamic memory, from one object to another without incurring the overhead of copying. This transfer is achieved through what are called R-value references. An R-value reference allows us to bind to temporary objects R-values that are eligible to be moved from. So instead of copying values which can be expensive, we can move them, effectively transferring ownership and dealing with potentially lower memory overhead. Now let's take a look at how we can implement a class that utilizes move semantics to manage a dynamic array efficiently. In this moveArray class, we define a constructor that allocates an array of integers on the heap, initializing it with values based on their indices. This approach guarantees that our array is ready for use right after instantiation. Next, we have a destructor that ensures proper memory cleanup by deleting the allocated array when the object goes out of scope, preventing memory leaks. Moving on, we introduce a move constructor that enables the transfer of the array's ownership from one moveArray instance to another. By taking an R-value reference, it can directly take the resources of a temporary object, leaving the original object in a safe state with its pointer set to nullter to avoid double deletion. To complement this, we have a move assignment operator that not only transfers ownership, but also manages any existing resources by cleaning them up before reassignment. This careful management of resources ensures that we maintain efficient memory usage without the overhead of deep copying, thus fully leveraging the benefits of move semantics for better performance in our applications. The displayed figure is a simple bar chart titled Impact of Move Semantics on Performance in C++ that compares two implementation methods, without move semantics and with move semantics. The chart shows a performance score of 80% for the implementation without move semantics and 95% for the implementation with move semantics, with the numerical values annotated above each bar. The clear pattern is a 15 percentage point absolute increase when move semantics are used, from 80% to 95%, which corresponds to an approximate 18.75% relative improvement over the non-move implementation. From this visualization, we can conclude that adopting move semantics yields a measurable and substantial performance boost in the presented scenario. The with move semantics case attains a notably higher performance score, indicating reduced overhead from resource transfers and more efficient handling of dynamic resources. The chart highlights that while both implementations achieve relatively high scores, the use of move semantics consistently improves efficiency and should be preferred in contexts where resource ownership can be transferred instead of copied. In this moveArray class, we have implemented both a move constructor and a move assignment operator. The move constructor initializes a new moveArray object by taking ownership of the resources from another object that is being moved. It crucially sets the other object's pointer to nullter to avoid the possibility of double deletion, where both the original and the new object try to delete the same memory. The move assignment operator works similarly, but first, it ensures that existing resources are released before taking over new ones. The noexcept specifier indicates that this operation does not throw exceptions, providing an optimization hint to the compiler, which can lead to better performance in some contexts. Now let's see how we can implement a practical example of using the moveArray class within a program. In this code, we define a function called createArray, which takes a size parameter and generates an instance of the moveArray class. Inside this function, we first create a temporary object, temp, to hold the array. This temporary object is then returned directly from the function. When we return temp, the move constructor comes into play, allowing the resources of the moveArray instance to be efficiently transferred to the variable r in the main function. This transfer of ownership avoids the costly overhead associated with copying the underlying dynamic array. Instead of duplicating the data, the pointer and size are moved, leaving the original temp in a valid but empty state, a critical aspect of move semantics that helps prevent memory leaks and double deletion issues. Finally, as we call the createArray function in the main function, the code demonstrates how move semantics enhances the efficiency of resource management in C++. By eliminating unnecessary copies, this implementation showcases the power of move semantics in action, resulting in a more performant program. In this snippet, the function createArray generates an instance of moveArray and returns it. Thanks to move semantics, when this temporary object temp is returned by value, it doesn't necessitate a deep copy of its resources. Instead, the move constructor is invoked, efficiently transferring the ownership of the internal array to the R variable in main. Now let's see how we can implement a function that utilizes the moveArray class we've discussed. The createArray function creates a temporary moveArray object initialized to a specified size. When this temporary object is returned from the function, thanks to move semantics, the ownership of its resources, specifically the dynamically allocated array, is transferred to the variable in the calling context rather than being copied. This is crucial because without move semantics, returning temp would invoke the copy constructor, leading to the overhead of duplicating the dynamic array and incurring unnecessary resource consumption. Instead, the move constructor is called, efficiently transferring the internal pointer and size to the new instance while leaving the temporary object in a safe, reset state with its pointer set to nullter. In the main function, we see an application of this, where createArray is invoked, and the result is assigned directly to the R variable. This simple yet powerful mechanism showcases how move semantics can enhance performance by reducing the need for costly deep copies, allowing for a more efficient handling of dynamic resources. Now let's take a look at how we can implement a function that utilizes move semantics with the moveArray class. The function processArray is defined to accept an R value reference to a moveArray object, denoted by moveArray and an R. This allows the function to accept temporary objects efficiently, enabling us to manipulate the array without the performance cost associated with copying. Inside the processArray function, we can directly access the properties of the moveArray object and perform operations on it. For instance, a simple output statement displays the size of the array by calling r_getSize. This direct manipulation emphasizes the advantage of move semantics, where ownership of resources is transferred rather than duplicated. Next, we will see how we can utilize this function by passing a temporary instance of moveArray, created on the fly with the expression moveArray5. This example illustrates the power of move semantics, as the temporary object is moved into processArray without incurring the overhead of a copy, allowing for efficient resource management. This efficiency is crucial in performance-sensitive applications where resources are costly to duplicate. Now let's take a look at an example that highlights the efficiency of move semantics using a class named Big Data. This class encapsulates a std, vector of strings, which can be costly to copy, particularly when dealing with large data sets. Here, we define a constructor that initializes the vector to a specified size. Next, we implement the move constructor, which leverages the std move function to transfer the ownership of the vector from a temporary object to the new instance. This is a crucial method because it allows us to avoid deep copying the vector's contents, setting the original object's vector to a safe, empty state. This means that when an object of big data is returned from a function, the vector is not duplicated. Instead, its ownership is moved efficiently. Now let's see how we can use this big data class in practice. The function createBigData creates a temporary big data object initialized with a specified size and then returns it. Because of the move semantics, this return operation invokes the move constructor, resulting in an efficient transfer of the vector without the overhead of copying. In the main function, we demonstrate this by calling createBigData and capturing the returned object. Thus, we achieve high performance when working with large data structures while maintaining clean and efficient code. In this scenario, passing a large vector of strings would otherwise invoke costly copies. With move semantics in place, we efficiently transfer the vector's ownership on construction and return, overriding the need for expensive copying operations. To summarize, move semantics is an invaluable tool in the C++ programmer's toolkit, enabling developers to write more efficient and performant code. By transferring ownership of resources rather than copying them, we not only save on time but also on the memory usage of our program. This ultimately leads to cleaner, more maintainable code. To wrap up, adopting move semantics requires a solid understanding of R-value references, proper implementation of move constructors and move assignment operators, and an awareness of when to apply these concepts within your code base. Embracing this paradigm shift can lead us to develop robust applications that stand the test of efficiency in high-performance scenarios. As we continue our journey through advanced C++ memory management, we will further explore topics such as perfect forwarding and smart pointers in conjunction with move semantics, enabling us to write even cleaner and more efficient code. Stay tuned for more insights and strategies to enhance your C++ programming skills. In this final section, we will do a project challenge to apply what we have learned so far. The objective of this project is to create a memory management system in C++ that mimics simple allocation strategies like first fit and best fit. You will implement a basic memory allocator that can allocate and deallocate memory blocks of various sizes, create a sample class to manage objects such as an employee class, and ensure proper memory management by implementing a memory leak detector. Additionally, you'll explore the use of smart pointers, such as unique PTR and shared PTR, to efficiently manage the life cycle of your objects while adhering to RAII principles. Along with your implementation, you'll prepare a report detailing your design choices, challenges faced, and the effectiveness of your approach. Remember to submit your code and documentation by the deadline, and you can find the full details of this project in the GitHub repository linked in the description.